Hello, everyone. Welcome to the fifth annual Design Engineering Competition. I'm Nicole Willett, the Director of Education for the Mars Society. When you are ready to start your presentation, please introduce yourself and your team, and whoever is speaking, please introduce yourself at the time of your speaking. You have 20 minutes to present. Any questions and answers should remain in the chat. So if students from other teams have questions, please put the questions and answers in the chat. If your team does not show up, they are disqualified from this competition starting today because the presentation is one of the most important parts of the competition. I received a large number of emails overnight, and those are going to be answered over the next couple of hours. So I would like to present Team Nova Lab. Are you ready?
Yes, we are ready.
Okay, you have the con.
Okay, hello everyone. First I need to sorry about my English accent, but I will try my best. Okay, first we need to select about the location. We check. Wait a minute. Okay, first surface lava. No, just a minute. Okay, about the location, we have to park is a Elysium Planetier. Yes, because it's perfect to park in there. Okay, we select this location based on NASA research. And over 7 missions you see on the screen. Yeah, this area is the best for spot of our building habitat and landing our spacecraft because it sits right in center of our base and all 7 missions. Site in is very short, making our operation highly efficient. Moreover, Elysium Planetier is a very flat and low-lying plain. This makes it a safe place for spacecraft and rover movement. Most importantly, it perfectly supports our first 4 missions for lava exploration and underground living. This area has an anti-lava tube that can naturally protect our krill from harsh space radiation and extreme cold. Okay, select. Next slide, please. Next, um, next, next slide, please. Next. Okay, next. Next slide, please. This is a picture from Elysium Planetier. Is the soil have a base for planting on a plant? Yeah, on about plant we can plant in there because it have a great soil about a pH value, something like that. It's like earth. Yeah. Next slide, please. Move on the next. Sorry for okay. So here, this is a space habitat that we are need to point on the Mars. Yeah, it's called Marshall, a design that won the first place in NASA 3D Print Habitat Challenge. I find this design very interesting for a few key reasons. First, as you can see from the screen, the picture, it looks like a few real, real home on Earth. When people think of a space habitat, they often imagine a small, crowded, and uncomfortable space. But Marshall is different. It is tall and open and filled with natural looking light. This open design helps reduce stress and make the grill feel comfortable. Okay. Second, the structure can be completely built using 3D printer technology with local machine material. Inside it has a very unique design into functional zone, private bedroom, a living room, a kitchen, and a bathroom. Living in a good environment that feels like a home without feeling crowded is very important is keep a grill mental health in a great condition, which is a key mission success too. I think like that. Okay, next we will install a research lab nearby, not too far from our habitat. This lab we will focus on studying radiational resistant crops for space. Oh, next slide, please. Okay. Many scientific papers suggest that we can use the genes from the tardigrade, tardigrade or water bears. As you know, tardigrade are extremely tall creatures that can even survive in open space and handle high radiation levels. We believe their genes can help our plants survive that harsh Martian environment. Additionally, this lab will be used for many other purposes, such as researching how to extract and purify water from the Martian soil and ice for our daily use. Okay, now let's talk about some food. Next slide, please. I mentioned earlier, we will build an agriculture dome for growing crops. First, we will construct a dome over specific area, then improve soil condition. We choose the area near the Elysium planitia. Yeah, Elysium planitia. Because the top soil here is the easiest to adjust especially. Its texture and pH level is good like earth. After preparing the soil, we will start planting inspired by the movie The Martian. Yeah, The Martian, which is the great movie about surviving on Mars. We will decide to that our very first crop will be potatoes. Yeah, potatoes are strong and easy to grow and can adapt well to adjust Martian soil. Successfully growing potato mean we can produce our own um for okay. For the water, we need to nourish our plants. I will dive into the detail the next section, but for the sunlight, we definitely have it here since our base is located near the Mars equator. This region receives the maximum and most consistent sunlight on the Earth on the planet. Yeah, even though sunlight on Mars is weaker than on Earth, this is the best location to capture natural light for our plant to grow. Yeah. Next slide, please. Okay, so just wait a minute, please. I can recognize them. This is a MOXIE for convert the carbon dioxide in Mars to be an oxygen. Because in Mars we have too much carbon dioxide and we have less oxygen. But human need oxygen to use for breathing. So we will use this machine to convert carbon dioxide to be an oxygen to use in our our house or maybe in our mission. Yes, to help us can breathe. Yeah. Next. uh, next slide, please. Okay, here is the thermal vacuum chamber. Yeah, thermal vacuum chamber. Okay. from the research, I have seen about the soil have water inside, and yeah, we can to pack the water from the earth to go to Mars at all for using it have a many way to do like that. But we have to pack this machine to go with us and to convert soil to be an water. If you know the the soil in Mars have 2 to 3% of water inside, so we can convert them and we can get water for using and drinking. Okay. And one way to think about it, we can use the ice on the polar of the Mars, but I will get that will be last chance to do it because uh you know uh the ice on the polar has had a many chance to have something you can learning you can do knowledge for them, so we will not touch anymore with the ice if it's not very initially. Okay, next please. Okay, so this is one our mission to the exploration underground of the underground of the Mars on Mars. Mm. Because the because on Mars have more radiation, there's no something protect like Earth. So I think if we use a Martian home to point on Mars, I think someday it can will be destroyed by storm, by radiation, or by something. So I have idea for to dig in the underground, underground and build architecture inside them, and we can we can have a second home that we have to protection by a ground. Yeah. Next slide, please. Okay, so this is a picture of NASA to use a rover to exploration under the ground. Okay, next please. Okay, this is maybe it's a power system, power generation. Okay, next slide please. Next. Okay, where's my friend Balls? Ball.
Okay, let's talk about the brain of the wallet. You can hear me?
Yes, we are hearing.
Okay. On my you cannot simply call for tech support due to orbital distance communication latency can reach up to 24 minutes per trip or almost 15 minutes per trip, not to mention weeks or planetary breakout. Therefore, real-time control from Earth is physically impossible. All base must be 100% self-sustaining and autonomous. The biggest threat to machine computation is not just software bugs. It's cosmic radiation, solar storm, and galactic cosmic ray can smash into microchip, causing single event upset and critical bit fix. Instead of relying solely on heavy hardware sharding, We solve this using mathematical probability. As shown in Figure 4, we implemented a triple modular redundancy or TMR architecture. The system processes the exact same instruction through the independent radiation resistance processor. Using majority voting logic and or probability model, TMR equal 3R squared minus 2R. 3R squared minus 2R cubed. The system automatically filter out radiation indexes error before they cause data failure. Even our physical hardware layout is designed for mass efficiency, instead of launching heavy traditional lead shading from Earth. We wrap our main server rack inside a water wall using the Hobbytech ECLSS water storage. The hydrogen molecules in water are exceptionally effective at absorbing neutron radiation, giving us maximum protection with zero waste payload weight. Finally, to manage the station, our central AI runs an autonomous FDIR system for detection, isolation, and recovery by operation real-time digital twin simulation using edge computing sensor. The AI tracks requirement role and share under total ionizing. Thus, it predicts failures before they happen, alerting the crew for proactive maintenance. This is not just a computer, it is efficiency or 7 crew members keeping the base alive. Thank you.
Okay, so now let's look at our powers and inflection system. We calculate everything based on the worst case scenario. For the maximum safety, the total mass of our 5-score system is approximately 8,920 kilogram, requiring 20 to 40 kilowatt of power. First, power generation. We use a hybrid system first to 10 kilowatt nuclear reactor, massing 3508 kilogram, provide continuous baseline power. Second, a high efficiency solar array with a egg sheet massing 1333.36 kilogram support the daytime load 2000 generation mass many kilogram. Okay. Second, power storage for Fortnite power. We use a 311.53 kilowatt hour solid state battery massing 778.83 kilogram. Combine the complete power system mass 5,620.19 kilogram.
Hello, hold on one moment. You have 2 minutes left. 2 minutes.
Okay. We have more about the power, but we will skip into the human operation. Okay, so skip please. Okay, about the human operation. Finally, let's look at a human operation. In this section, our team focused deeply on the space physiology and managing the crew mentioned well-being throughout the long-duration mission. The biggest threat on the Mars is often isolation and mental fatigue. To tackle this, after field operation and in 17, the crew gather for the dinners and daily debrief. But the most critical part happened during on our evening routine group session. This acts as an icebreaking and alignment session designed to smooth out attitude, build deep mutual understanding, and nuclear any high tension between the be sorry yeah between the crew and the station controller. Furthermore, maintaining a connection to Earth is vital for survival. The station controller regularly shares future news and updates from home. By combining the dynamic team combination, personal emotional outlet, and a continued bridge of information back to Earth, we ensure our crew mental health remains stable, resilient, and ready for mission success. Okay, so today our team Novalab has already for presentation. Thank you everyone for listening. Thank you.
You guys did a wonderful job. Thank you so much. Please stop sharing your presentation. The next presentation is from a group of students who pre-recorded their presentation, so I will be sharing that. Remember, if you have questions for the teams, please keep that in the chat for now. And we will be critiquing each other. We will be critiquing each other's missions on Wednesday, so 48 hours from now. So take notes so you understand the critique portion. Usually doesn't take as long as the presentation portion. So the next presentation is, let me share my screen.
Hi, Nicole. The students are also logged in. This was recorded just in case if they have some internet issue. So
Oh,
if
so do you want them to
yeah,
present themselves?
yeah, sure.
Okay, okay. My apologies. I misunderstood. Go ahead. They may share their screen and get started. Make sure they introduce themselves and their names, please. If they're talking, we cannot hear them.
Hi everyone, my name is Aksa and today I will explain about introduction of Mars. Respected judges, teachers and your audience, thank you for giving this opportunity to present our Mars mission design. Our team name is AD Mars Pioneers and our mentors are teacher Nival and teacher Minahil. Our team members are Aksa, Simab and Umme Kulsoom. Today we will present our complete Mars mission design which explains how astronauts can safely travel from Earth to Mars. Live there for several months, carry out scientific research, and return safely to Earth. Our mission is not just a theoretical idea, we have designed it as a realistic future mission by combining science, engineering, and human operations. We have also included practical solutions for the challenges astronauts may be faced living on Mars. Now, let's begin with the mission overview. Next slide. Our mission has 5 main objectives. The first objective is to transport astronauts safely from Earth to Mars. For this, we have designed a spacecraft with life support system, radiation protection, communication system, and safe landing technology. The second Objective is to establish a self-sustaining habitat on Mars. The habitat will provide astronauts with oxygen, water, electricity, food production, medical facilities, and a safe place to live. We have also including recycling system and ISLU technology so that astronauts can use local Martian resources instead of depending completely on Earth. The third objective is to conduct scientific research. Our astronauts will study Mars geology, climate history, rocks, volcanoes, and ancient rivers to better understand how the planet formed and changed over billions of years. The fourth objective is to explore water resources and search for signs of past or present life. We will use advanced scientific instruments to detect underground ice, collect samples, and analyze them inside our habitat laboratory. Finally, our mission will test new technologies such as autonomous robots, drones, water extraction system, oxygen production, and sustainable life support system. These technologies will help prepare for future long-duration human mission and permanent settlements on Mars. Next slide. No, नो ये वाली स्लाइड नहीं है. Okay. Mars is the fourth planet from the Sun and it is often called the most Earth-like planet in our solar system. Although it is much colder than Earth, it has many features that make it one of the best places for human exploration. Scientists have discovered water ice beneath the surface, changing seasons, volcanoes, valleys, ancient river channels, and dried lake beds. These discoveries suggest that billions of years ago, Mars may have had a warmer climate and flowing water. This is one of the main reasons why scientists are interested in exploring Mars. By studying its surface, climate, rocks, minerals, and water resources, we can better understand how the planet's history and investigate whether life ever existed there. Our mission design provides a realistic and practical plan for traveling to Mars, building a safe habitat, using local resources, conducting scientific experiments, and helping astronauts live and work safely on the planet. We believe that this mission can become an important step towards future human exploration and the possible settlements of Mars. Next slide. Every Mars mission must be launched at the right time. We cannot launch whenever we want because Earth and Mars keep moving around the Sun. Our mission will launch during the best launch window, which occurs about the 26th month when the two planets are in the most suitable positions. Launching during this period reduces the travel distance, saves a large amount of fuel, and shortens the journey to about 6 to 7 months. It also reduces mission cost and lowers the risk for the astronauts. Before launch, we will carefully check the spacecraft weather conditions, life support systems, fuel levels, and communication system to make sure everything is ready. Choosing the correct launch window gives our mission the highest chance of reaching Mars safely and successfully. Thank you.
Is there more to your presentation?
Hi everyone, I'm Ravi Azam and I'm talking about landing site and site. Selecting the right landing site is one of the most important part of our mission design. After studying different regions of Mars, we selected Arcadia Planitia because it meets almost all the requirements for a long-term human mission. This area contains large underground ice deposits, which can provide us drinking water, oxygen, and hydrogen fuel through ISRU technology. And other advantage is that the surface is wide and relatively flat. This makes spacecraft landing much safer and also provide enough space habitats, solar panels, and scientific work. Before landing, our spacecraft will scan the surface using cameras and sensors to avoid large rocks and dangerous areas. After landing, drones and rovers will inspect the area before astronauts begin building the habitats and starting scientific research. Next slide. Next slide. Living on Mars is very challenging because its environment is completely different from Earth's. The atmosphere is very thin and is made mostly of carbon dioxide, so astronauts cannot breathe without life support system. The average temperature is around minus 60 degrees Celsius, although it can become even cooler during night. Mars also has only 38% of Earth's gravity, which can weaken muscles and bones during long missions. Another challenge is powerful dust storms that can reduce visibility, cover solar panels, and damage scientific instruments. To overcome these challenges, our mission includes a pressurized habitat, reliable power sources, water recycling system, and daily health monitoring system. These systems will help astronauts live and work safely throughout the mission. Next slide. Let's shift. Geology and history. One of the main scientific objectives of our mission is to study the geology and climate history of Mars. Scientists believe that billions of years ago, Mars had a warmer climate, flowing rivers, lakes, and possibly a thicker atmosphere. To understand how the planet changed over time, our astronaut will explore different rock layers, volcanoes, minerals, and ancient geological formations. Using drones and rovers, we will first survey the area and identify scientifically important locations. Then astronauts will collect rock samples from both the surface and underground using robotic arms and drilling equipment. The collected samples will be analyzed in our habitat laboratory using microscopes, spectrometers, and other scientific instruments. If we discover minerals that only form in the presence of water, it provides strong evidence that Mars has once a much wetter environment. This research will help us understand the geological evolution of Mars and also identify suitable location for future human settlement. Next slide. Next slide. Water is one of the most important valuable source on Mars. We will use ground penetrating radar, neutron spectrometers, and thermal cameras to detect underground ice and water-rich areas. After identifying suitable location, astronauts will use a drilling machine to collect soil, rock, and ice samples from different depths. These depths will be transported safely to the habitat laboratory where they will be examined using micrometers, chemical analyzers, and spectrometers. Our scientists will search for organic molecules, hydrated minerals, and other biosignatures that may indicate whether binomial life existed on Mars in the present or could exist today. If any important evidence is found, the sample will be preserved for future mission and possibly returned to Earth. What?
Hello everyone, I will explain scientific research and ISRU. Scientific research and ISRU. Our mission is not only about exploring Mars but also about preparing for future human settlements. Throughout the mission, we will monitor radiation, weather, temperature, wind speeds, and dust levels using advanced scientific instruments. At the same time, we will test ISRU, which stands for Instru Resource Utilization. This technology allows astronauts to use Martian resources instead of depending completely on Earth. Underground ice will be extracted, melted, purified, and converted into drinking water. Using electrolysis, water will also be separated into oxygen for breathing and hydrogen for future rocket fuel. Testing these technologies is very important because they will make future Mars missions more sustainable, safer, and much less expensive. Next slides. Mars habitat. Our habitat will be the astronauts' home on Mars, so it must provide a safe and comfortable place to live and work. After landing, robotic system will first inspect the landing area and prepare the ground. The habitat modules will then be unloaded from the spacecraft and connected together to form one complete living station. Once the habitat is assembled, robotic vehicles will cover it with Martian soil called regolith. This natural layer will protect the crew from harmful radiation, micrometeorites, extreme temperatures, and dust. Inside the habitat, life support system will automatically maintain oxygen levels, air pressure, temperature, and humidity to create an Earth-like environment. The habitat will include sleeping cabins, a laboratory, a medical room, a kitchen, storage areas, a hygiene section, an exercise area, and a communication room. Our habitat will also have a modular designs, which mean that additional sections can easily be attached in the future as more astronauts arrive and new facilities are needed. This design makes the habitat suitable not only for our mission, but also for future Mars settlements. Next slides. Life support, water and food system. Long-term survival on Mars depends on reliable life support, water and food system. Inside the habitat, the life support system will continuously clean the air. Carbon dioxide released by the astronauts will be removed using carbon dioxide scrubbers, while an oxygen generation system will supply fresh oxygen. Sensor installed throughout the habitat will continuously monitor oxygen level, air pressure, humidity, and temperature. If any value change, the system will automatically adjust it to keep the environment safe. Water will come from two sources. One, underground ice will be located using scientific instruments. A drilling machine will extract the ice, which will then be melted in an ice melting unit. The water will pass through filters and a UV sterilization system before being stored in tanks for drinking, cooking, hygiene, and scientific use. Second, wastewater from washing, cooking, and moisture collected from the air will be recycled using a water recovery system. This will reduce water waste and provide a continuous water supply. Fresh vegetables such as lettuce, spinach, tomatoes, and herbs will be grown inside a greenhouse using a hydroponic system, where plants grown in nutrient-rich water instead of soil. LED grow lights will provide artificial sunlight, while automatic sensors will control water, nutrient, temperature, and humidity. These plants will provide fresh food and also help improve air quality inside the habitat. Next slides. Power system. Every mission system depends on a continuous and reliable supply of electricity. After landing, the solar panels will automatically unfold and begin converting sunlight into electrical energy. This electricity will power the habitat, laboratory, communication equipment, life support systems, greenhouse, and scientific instruments during the daytime. Because Mars has long nights and frequent dust storms, our mission will also use a small nuclear reactor. The reactor will produce electrons continuously regardless of weather or sunlight, ensuring that all essential systems remain operational at all times. A power management system will distribute electricity to different habitats according to their needs. Backup batteries will store extra electricity generated during normal operation. If the solar panels or nuclear reactor temporarily stop supplying power, the batteries will automatically provide electricity until the main power source is restored. Using these three systems together, panels, a nuclear reactor, and backup batteries will provide a safe, stable, and uninterrupted power supply throughout the Mars mission. Thank you.
Hi everyone, myself Ume Kulsum. Today I am going to talk about Mars technology. Advanced technology will play an important role in every stage of our mission. Before astronauts being exploring autonomous, drones will fly over the area to capture high resolution images, create detailed 3D maps, and identify safe routes. Pressurized rovers will transport astronauts, scientific equipment, and collected samples across the Martian surface while protecting the crew from the harsh environment. Our rotary percussive drilling system will collect rock, soil, and ice samples from beneath the surface for scientific analysis. These samples will then be transported safely to the Habitat laboratory for detailed examination. The communication system will allow the crew to exchange information with mission control on Earth. Even though there will be a communication delay due to the long distance, our mission will also demonstrate ISRU technology by extracting underground ice, purifying it into drinking water, and producing oxygen through electrolysis using Martian resources instead of depending entirely on Earth will make future human missions more sustainable and cost effective. Next slide. Crew selection and living on Mars. Now, let us talk about the people who will make this mission successful. A Mars mission cannot be completed by one person. It requires a highly trained team where every member has a specific responsibility and also knows how to support the others when needed. Our mission includes 4 crew members. Aksa will serve as the mission commander and will lead the entire mission. She will coordinate daily activities, make important decisions, and maintain communication with mission control on Earth. Sima will work as the systems and engineering officer. She will maintain the habitat, power systems, communication systems, rovers, and all scientific equipment. If any technical problem occurs, she will diagnose and repair it to keep the mission running safely. Rabia will be the science and research officer. She will lead geological studies, search for water, collect rocks, soil, and ice samples, and supervise all scientific experiments. She will also analyze the collected data and prepare important samples for future study. Ume Kulsum will be the medical and life support officer. She will monitor the crew physical and mental health, provide medical care when required, manage food and water supplies, and that ensure oxygen, air quality, and life support systems continue to operate properly. Before traveling to Mars, every crew member will complete extensive physical, technical, and emergency training. They will learn how to operate spacecraft systems, use scientific instruments, drive rovers, perform drilling, collect samples, and respond to medical or technical emergencies. Living on Mars will require discipline and teamwork. Next slide. Health and human adaptations. Living on Mars is very different from living on Earth. The crew will face low gravity, high radiation, extreme temperature, and long periods of isolation. Therefore, protecting the astronauts' health will be one of the highest priorities of our mission. Mars has only 38% of Earth's gravity. Because of this, astronauts may lose muscles, strength, and bone density during long missions. To reduce these effects, every crew member will exercise to about 2 hours every day using a treadmill, resistant exercise machine, and stationary bicycle inside the habitat. Their health will be monitored regularly so the exercise program can be adjusted if needed. Radiation is another major challenge because Mars has a very thin atmosphere and no global magnetic field. To protect the crew, the habitat will be covered with Martian soil called regolith, which acts as a natural radiation shield. Each astronaut will also wear a personal radiation monitor and radiation sensors around the habitat will continuously measure radiation levels. During a solar storm, the crew will immediately move to a specially protected radiation shelter. Regular health checks will include monitoring heart rate, blood pressure, oxygen level, body temperature, and overall physical condition. Next slide.
You have
Safety
about
and
30,
emergency
you have
development.
about 30 seconds. 30 seconds till the next team. If the next team is here, please let me know.
Safety is one of the most important parts of our mission design, our Mars mission design. Every system has been designed to protect the crew during both normal operations and unexpected emergencies. When our astronauts leave the habitat to explore Mars, they will wear advanced pressurized spacesuits. These suits will provide oxygen, maintain body temperature, protect against harmful radiation, and prevent Martian dust from entering the suit. Before every EVA, the crew will carefully inspect the spacesuits, communication devices, batteries, oxygen tanks, and emergency equipment to rovers whenever traveling long distances. During every VA, mission control and the mission commander will continuously monitor the astronauts' location, health, and communication systems. Mars is also known for powerful dust storm. Our habitat will include a protected emergency shelter where astronauts can stay safely until the storm passes. Thank you.
Our mission combines science, engineering, and human operations to help astronauts travel safely, live on Mars, and conduct valuable scientific research. We have carefully planned every stage of the mission, from landing and habitat constructions of water production, life support, and crew safety. We believe that this mission design can support future human exploration and the possible settlements on Mars. Thank you for your attention.
Wonderful, wonderful, very well thought out presentation. Thank you so much. The next team is here and ready. So if you could share your screen, we'll get started right away. Make sure to introduce your team and your team name.
Hi everyone, we are MESA, short for Mars Exploration and Settlement Agency. Oh, sorry, 1 second. We are investigating whether Mars has a suitable environment for long-term human exploration and future settlements. Our research will focus on identifying essential resources such as minerals and elements that could support construction, protect against radiation, and help build life support systems. We also studied the natural features. We will also study the natural features such as lava tubes, frozen lakes, and craters that may offer natural shelter from radiation, extreme temperatures, and dust storms. Our three main objectives are studying Mars's geology and mineral composition to identify useful resources, explore lava tubes as natural shelters from radiation and extreme weather, and to evaluate the habitat, power, and life support systems for future settlements. Our aim is to bring back findings to compare with minerals from Earth, and these are the constraints we worked around. We evaluated the planet and came back with four main problems. Those four main problems were dust storms, craters, terrain, and petrolates. The location we picked was based on its geological and scientific value. The four main values we picked were geology, climatology, paleontology, and astrobiology. And we picked these 5 drilling sites to explore our objectives. So we'll use water ice, paleoclimate, mineralogy, geology, and biosignatures and atmospheric history to study the composition of Mars and see if it aligns with our objectives. For sample collection, we will use a geosatellite drone to canvass the area, and during EVA excavations, the Marsonauts will use tools such as hammers, drills, and air scribes to dig up rocks and ice. They will use a shovel to collect soil samples, and robots will help in areas that may be dangerous and hard to get to. Each sample will be sealed in a container and placed in an airtight, sterile chamber in the habitat, labeled with location, date, and time. To save energy, we will also be using rovers to bring everything back to the habitat. Samples will be analyzed in the laboratory using chemical analyzers and a microscope. After researching, we found 4 main areas to focus on to make sure our mission goes safe and smoothly. The first one is redundancy. To do this, we'll be duplicating our systems, so if one fails, another one will start automatically. The second one is testing both hard and software to make sure it is sustainable in Mars-like conditions. And the third one will be making sure our spacecraft will operate independently. By doing this, we have a built-in decision making, and it will handle any emergencies, and it also have a fail-safe design to stay stable. For our first launch, we decided to split our launches into 2 groups. This is based on Elon Musk's approach to exploring Mars. He talked about using a mix of robots and heavy industrial machines to prepare the habitat before launch. We will be following his initiative and using a mix of robots such as Optimus, his own design, and NASA's Athlete for tasks such as moving metals and basic assembly, alongside managing excavators, drilling, and setting up base. We will also have rovers that are adapted to operate without human control and make them do most of the research on the terrain. For our first launch, we're estimating around 19 tons, including IRSU, power systems, and an inflatable greenhouse. This is what we are envisioning our base will look like after robots have come to set up before us arriving. For our second launch, it will include the crew members, the habitat module for inside the lava tubes, which we will be experimenting on, and any scientific equipment. Because the infrastructure is already built, so launch will focus on experimenting living conditions on Mars, such as lava tubes or craters, and allowing the crew to focus on conducting their research. This launch will estimate around 12 tons, such as the habitat modules, the science equipment, and space gear. The first crew member will be a commissioner and a system engineer. He will specialize in mechanical engineering, understanding power and electrical systems, and will be responsible for coordination, critical decisions, and keeping the mission safe and organized. The second member will be a medical officer and a biologist. She will specify in first aid, emergency care, testing water quality, and understanding microbiology of the planet. The third crew member will be a pilot and a geologist. His main skills would be space operations and navigations, also focusing on drone and robotic operation, and will be able to analyze samples, all the samples we have collected and safely operate the spacecraft and lead the EVA explorations around Mars. Training before the mission. The first one will be that the crew members will be given special training to withstand the atmosphere pressure and the lack of gravity. The first training will be in underwater pools with ankle weights that are similar to the weight of their spacesuits to get them used to long and hard spacewalks. The second one will be robotics. The crew member will be able to practice playing around with a simulation on controlling the robot's arms and using them to precisely excavate materials. The third one would be emergency drills. The crew will be placed in emergency drills such as fires, air leaks, medical emergencies, and storms to make sure they are fully aware and prepared to help with anything that goes wrong. The fourth one will be building exercises between the crewmates to get them used to each other, develop communication in order to reduce conflicts and stress on the mission. The fifth one is survival training, and the crew will be put in different environmental simulations to prepare them for any type of emergency landing. The sixth one will be medical training. Although we have a medical member in the crew, all crew members will also be taught basic first aid just in case anything happens. We will be mainly using robots for repairing our habitat, but all crew members will also be taught how to use the system engineer, and the system engineer will have knowledge and understanding of repairing any systems and equipment. The last one is all crew members will have to have a driver's license and be taught how to drive the rover safely on the rough terrain on Mars. For our spacesuit, we decided it was best for a hybrid design. The hybrid design would be a mix between the Ayuda spacesuit, NASA's X-EMU suit, and the SpaceX concept. The suit will function like a mini spacesuit and provide 6 to 8 hours of oxygen and removing CO2. It will also be a fully sealed suit, and it will have a hard upper torso with flexible and sealed joints to help with mobility, and will have a helmet which includes a HUD, showing navigation oxygen level warnings such as leaks, dust storms, etc., messages for mission control, and more. The suit will also have an anti-dust coating as well as due to dust being fine and toxic, and will also have self-cleaning surfaces. Overall, the hybrid design will focus on making exploration more practical while keeping the crew members safe. EVA operations and frequently asked questions. How long will the operations last for? We have estimated 48 hours per week, 48 hours per excavation, and we'll do 2 to 3 per week. Why would we need this? This is to collect rock samples, repair base and equipment, and also set up scientific instruments. We will have the crew members go in groups with the robots for explorations that are further away, but with explorations close to the base, we'll only have one member going out. The habitat will provide sleeping areas, which are private cabins for each member. We'll have a medical lab, which is supplied with medical tools and things used in emergencies, such as a fire extinguisher. The third one will be a kitchen and an exercise area, which is filled with weights and a compact treadmill for each member to use. We will also have a greenhouse, which is used to grow vegetables, which we'll be testing on the Mars environment. And we'll have an airlock sealed chamber on each side of the lava tube and the habitat on top of ground. There will also be a control room, which is filled with monitors and data with every information that we found and every information based on the crew member. And there'll be emergency shelters just in case there is a dust storm, a radiation storm, or there's a hole in the habitat that needs to be patched up. We have found that there are 3 different power supports, and our first one will be solar power. We will have large solar powers near and around the habitat, and there will be robotic cleaners to clean any accumulated dust overnight. Advantages of using solar power is that it's renewable, it's easy to expand as we grow our base, but the disadvantages are that there's no power at night, and during storms there will be a blackout, so we'll have to use our secondary source, which is a nuclear reactor. This is a compact nuclear fission reactor, and it provides continuous electricity regardless of weather or time, and it keeps critical systems running during dust storms. Just in case anything happens, we'll also have a backup source, which is batteries, and those are large lithium-ion or solid-state batteries used for emergency power only. Surface logistics for the crew. All supplies are transported from the landing site to the habitat by cargo rovers. All supplies are tracked with computers and inventory systems, so we know how much supplies we have, if we need any more, and if there's anything missing. And all heavy equipment is moved using robotic systems, cranes, or cargo rovers, which will reduce risk of injury. Life support systems. Oxygen will be produced by IRSU and will be used by splitting water from hydrogen and oxygen. There will also be CO2 removal, which are special filters to remove carbon dioxide from the air so our astronauts can breathe safely. Water recycling will be all reused and cleaned before we drink from it. And then there would be pressure control. So because of the airlock chambers, we'll make sure the pressure inside the habitat is safe for our crew members to walk around in. For food and water, all food will be mostly freeze-dried or packaged, and we'll have backup supplies in case farming fails or just in case the astronauts do not like the food that we have already. In terms of farming, we will be growing our own food on Mars, as this will let us understand how to control the environment and change any plants and any changes the plants may face. The 5 main questions are: would it be chemically different? As gravity on Mars is 0.3 grams, water and nutrients may move around differently. Plants may show differences such as starch distribution, thickness, and size. How would the radiation on the planet affect the plants? Will there be an increase in antioxidants? Genes will be different, or will there be different levels of chemicals that grow within the plant? The soil differences. If we process regolith, it still lacks earth biology, so it may contain toxins, and we would like to understand what those toxins will be. How would artificial light affect it, and will it still be classed as Earth's food? The 4 crops we will be testing first are potatoes, carrots, lettuce, and tomatoes. Potatoes are high in vitamin C and B6. They are high in calories and they boost immune systems, and they are high in antioxidants. Lettuce is high in vitamins A, K, and B9. They help with bone health and they boost immune systems. Carrots are high in vitamins A, K, C, and fiber. They are also high in antioxidants, boost immune systems, and help with bone structure health. Tomatoes are high in vitamin A, C, K, and potassium and help regulate nerve signals for our crew members. They boost the immune system and they're high in antioxidants. Waste recycling. We will be using a closed loop system, which means nothing is thrown away. Water will be recycled from showers, urine, air moisture, and water waste, which is purified using IRSU. And we have researched that there is a 95 to 98% recovery of all water. Organic waste will be using food scraps to turn into fertilizer at different strengths to test the conditions of farming and how it would affect the plant's growth. All plastic will be recycled, melted, and processed and reused into 3D printers to help make tools so we do not rely on extra equipment. All metal equipment will be smelted and reformed into new components, and any metals we find on the planet that is new or undiscovered, we will keep for research. Hazardous material and items that are covered in radiation will be sealed, stored, and either processed carefully or put away to dispose on Earth. Emergency procedures. We made a list of most common emergency procedures, such as any fire drills. We will sound the alarm in the system and put out the fire to isolate the area. Loss of pressure will seal the leak, close any hatches, and move to a safe area. Oxygen failure will use to back up oxygen and will get the robots to quickly repair the system while using tanks. Any water system failures will use emergency water supplies and will fix the recycler. For the crew's daily routine, it is recommended to exercise at least twice a day while in space, but we have only put down 1 exercise slot, as the crew will also be walking around a lot, aiding to the exercise. So we've estimated that around 7 a.m. the crew will wake up, get ready for the day. Around 9 a.m. they'll have their first EVA mission to explore the surface. Lunchtime will be lunch and rest, and they get to send messages to their family. And then from 7 o'clock to 6 o'clock, that's their time to exercise to maintain muscle, to do health checks, and they can choose to do an intense or light exercise. and around 9 p.m. onwards is time to allocate it for sleep, as we would estimate 8 hours of sleep for preferred mental health and physical health. Communications with Earth. We'll have daily updates so the crew can send reports on health, science, and equipment to the mission control system. They will also have family contact. They will be able to video and send voice messages to their family, which are pre-recorded, and although they're sent with a time delay, they will still get to talk to their family. Any backup systems will have spare communication equipment if available if the main system fails, and all the science data will be photos, videos, experiments, which are also sent to the control system on Earth. Exercise. The crew will focus on running on a treadmill, resistance training, weight exercises, flexibility, mobility training, and they will focus on balance and coordination to help with the lower gravity. Exercise is important, especially while on Earth, to prevent muscle loss, bone loss, cardiovascular deconditioning increasing. Each crew member before we launch will have their own personalized workout routine, which will be made during the health checkout before launch, so we know how to keep them in shape and what they need to stay healthy. Mental health. To ensure that the crew members stay physically and mentally healthy, here are some ways to reduce stress, fatigue, and isolation. They will have regular communication with their family, even if the communication is delayed. They will have an augmented reality, which will provide entertainment such as movies, relaxation, games, and books, and they'll have a structured, balanced routine and any group activity to help with isolation, such as celebrating birthdays. We'll also start our innovation center. So our augmented reality systems will be built into their helmets, so they will be displayed in the habitat to provide astronauts with their information, entertainment, and training methods. By using this, we can reduce the need to bring separate devices for each area, and it'll be more efficient during operations. We want to implement AI assistants to help in the spacesuit, spacecraft, and habitat to assist the crew members. It will also act as a constant support system, keeping tabs on the health, suit status, and any damages, and all that information will be sent to the main control system. And the suit will also be able to warn crew members about their oxygen levels or any damages to their suits. The last thing is we will want to use 3D printing to help manufacture tools, spare parts, or equipment so we don't have to bring them with us. We'll create filament by recycling plastic and metal as the operation goes ahead. This also helps speed up the operation, as crew members will not have to wait for resupply missions, which could take time and are expensive to send out. Using 3D printing, we can also expand the habitat, create components for scientific research and experiments, or it can be used to start developing the terrain. Overall, our aim for the crew is to be on Mars for 69 months and leave the rest for the robots there. And we'll check on them via connection and doing service trips at least once a year. The crew will return with all the samples they gathered, information or anything of value, and will continue to conduct the rest of the research on Earth. These are the main groups we would like to thank: the Hypatia Mars Association, the UAE Space Agency, and the Austrian Space Forum, and Patrick Martin, Captain Mohammed, Ravi, and Nandini Rega for all the interviews we conducted. That's it. Thank you very much.
Perfect timing. Thank you so much for that wonderful presentation. Our next team is here. We will, do you guys want to start a couple minutes early, or does everybody need a break?
I don't know.
Pardon?
We can start early, no problem.
You can start early, okay. Make sure you introduce yourself and your team, and whoever's speaking, make sure you are introducing yourself, and you have 20 minutes.
Can you see my share screen?
Yes.
Okay, perfect. My name is Bogdan, and I'm with Project Great Horizon. First, I would like to start with an introduction. Humans have always looked to Mars and thought about building a civilization there. Our mission focuses on testing the grounds on Mars for future self-sustainable colonization. Before we send our mission to space, we have to carefully analyze our objectives. Blindly sending humans to Mars is a failure of logistics. To ensure the survival and well-being of our crew and future humans on another world, we must move away from the normal style of exploration and move towards safe to self-sustaining infrastructure. You're muted.
We can't hear you.
Oh, sorry. So now I will explain why we choose Arcadia Planitia as our landing site. So choosing a landing site is one of the most important things that we can do in our Mars mission. And this location needs to be a safe location, and we should be able to access important resources and this place should support the long-term human operations. So after comparing different regions on Mars, we chose Arcadia Planitia because it has been identified by NASA's and SpaceX as one of the best places. Why? The first reason is water ice. So data collected by NASA's Mars orbiter Sharad radar instrument shows that Arcadia Planitia has almost continuous sheets of ice, like big ices. So, and it's extremely important for us because we're gonna need water for drinking, growing food, using electrolysis, like by dividing water to hydrogen and oxygen, then combining it by CO2 to make methane as a fuel to go back to the Earth. And a continuous sheet of ice is easier to access because we're not gonna need a lot of drilling for that. So that's why we choose the landing site Arcadia Planitia. The second reason is the terrain, the place that we're gonna land. Arcadia Planitia is one of the flattest regions on Mars, and it reduces the risk of landing, of hazards, and of course it's so much easier to land in the flat place rather than in a place with a lot of rocks and cliffs. And another advantage is our low elevation, and because it lies at the low elevation, and it has the slightly higher atmospheric pressure than other places on the Mars. Mars has 10 atmospheric pressure, but this place has a little bit more, slightly more atmospheric pressure, and it's gonna help us landing, because of the drag there. So for our mission, we're gonna need send 2 rockets actually there to reduce the risk. So the second spacecraft will be sent 2 kilometers away. So first spacecraft will be the location of the first spacecraft will be 38.9 degrees north and 202.1 degrees east, and the second one is gonna go 39.8 degrees north and 202.1 degrees east. So because of the to reduce the risk. And in conclusion, Arcadia Planitia provides the a best combination of the of safety, accessible water ice, and suitable terrain to land there, and making it an excellent location for establishing a sustainable human presence on the Mars. That's it.
Now I'll give you an overview of our mission. So our mission uses a 2-launch strategy. So instead of sending the astronauts first, we send all the equipment needed to build a safe and fully operational base, which reduces the risk for the crew. And the first launch takes place in November 2026, and it carries the inflatable habitat, 3 nuclear reactors, the life support system, and 3 autonomous rovers. And after an 8-month journey, it lands in Arcadia Planitia in July 2027. We chose Arcadia Planitia because it has flat terrain. And as you've already heard, the ice is a really important resource because it provides water for drinking and oxygen production and fuel manufacturing. After landing, the robots will spend 16 months preparing the base. Since communication with Mars can take between 8 and 48 minutes, they work autonomously using cameras, while engineers on Earth send them daily instructions. The habitat inflates automatically, and the nuclear reactors provide continuous power. The rovers will extract ice, purify the water, and store it inside the habitats. Some of this water will be split into oxygen and hydrogen through electrolysis. The hydrogen will then be combined with carbon dioxide in a Sabatier reactor to produce methane fuel for the return journey. And 1 month before the astronauts arrive, the habitat will be heated, pressurized, and fully prepared. And then the second launch will take place in January 2029 and will arrive on Mars in August 2029. It will carry the 4 astronauts, food supplies, and EVA suits. The crew lands about 2 kilometers away from the habitat to avoid damage from rocket exhaust. And once they'll arrive at the base, they can immediately begin scientific work, including deep drilling, geological studies, and exploration using 2 Mars helicopters. And by separating the missions into 2 launches, we make sure the habitat is fully functional before people arrive, making the mission much safer and more reliable. Thank you. I'm done.
Next, let's look at our crew. For this mission, we selected 4 highly trained specialists, each with both a primary and a secondary profession. Having multiple skills is extremely important on Mars because help from Earth is millions of kilometers away and cannot arrive quickly in an emergency. Our commander and expedition leader is an aerospace engineer responsible for controlling the descent, landing systems, and heavy machinery. They are also trained as a secondary medical officer, allowing them to assist during medical emergencies. Our chief medical officer is a trauma surgeon and physician who oversees crew health, radiation exposure, and any medical emergencies. As a secondary role, they are also a botanist who manages the hydroponic greenhouse and food production. The chief science officer is an astrobiologist and geologist who leads deep core operations and analyzes Martian samples. They are also trained as a meteorologist, allowing them to monitor weather conditions, analyze shared data, and operate the mission helicopters. Finally, our mission specialist and operations engineer is a nuclear and systems engineer responsible for the reactors, power stations, and Sabatier fuel factory. Their secondary role as a robotics and AI specialist allows them to maintain rovers and carry out mechanical repairs. When selecting our crew, we looked beyond qualifications. We considered teamwork, adaptability, communication skills, and the ability to work under pressure. Since astronauts will be living together in isolation for long periods, compatibility is just as important as technical expertise. To manage disagreements, the crew will first try to solve issues through calm discussion. If needed, another crew member can act as a mediator. In situations that affect mission safety, the commander will make the final decision. Before launch, all crew members will also complete isolation training to prepare them for life on Mars. Now, let's move on to life support. Providing food, water, air, and power is essential for keeping our astronauts alive and healthy. At the start of the mission, most food will come from the Earth. This includes dried meals, dried fruits and vegetables, protein bars, nuts, and other long-lasting foods. These foods are lightweight, compact, and can be stored for long periods. However, for a long-term sustainability, our crew will also grow food on Mars using hydroponics, which is a method of growing plants without soil. Crops such as lettuce, spinach, tomatoes, and herbs can be grown using recycled water and artificial lighting. This provides fresh food, improves crew well-being, and helps support oxygen production inside the habitat. Water is another critical resource. Each astronaut is expected to use around 10 to 15 liters of water per day for drinking, cooking, washing, planet growth, and scientific experiments. Instead of transporting all this water from Earth, our mission uses an advanced recycling system similar to the one used on the International Space Station. Water from washing, breathing, and wastewater is collected and purified. We will also extract ice from beneath the Martian surface. The water then passes through 3 purification stages: a cyclonic separator to remove dust and break down toxic materials, and reverse osmosis membranes for final purification. Because the system recovers around 90% of the water used each day, only a small amount needs to be replaced from newly mined ice, making the mission much more sustainable. To power the mission, we chose nuclear energy instead of solar energy. Martian dust storms can block up to 99% of sunlight for months at a time, making solar panels unreliable. Our 3 nuclear reactors provide a total of 60 kilowatts of continuous power for mining equipment, habitat systems, scientific research, communications, and the hydroponic greenhouse. Finally, the habitat atmosphere will closely match Earth's air, consisting of 78% nitrogen, 21% oxygen, and 1% other gases. This creates a safe and a comfortable environment for the crew.
Okay, can you hear me?
Yes.
Now I'll present the habitat on Mars. For our mission, we chose the Mars-sized home inflatable habitat because it significantly reduces launch mass and has fewer transport restrictions than a rigid habitat. This makes it a more practical and cost-effective solution for a long-term mission to Mars. After landing, the habitat inflates automatically using compressed gas, while spring-loaded carbon fiber floor decks lock into place, creating a 2-story living space of approximately 158 square meters with multiple rooms for living, working, and well-being. And it also supports entertainment, which is really important for the crew. Next slide, please. Now I will talk about the habitat key functions. The habitat is made of several protective layers. The outer layer contains pockets filled with water that freeze into ice once on Mars. This frozen layer acts as a natural shield against galactic cosmic radiation, which is one of the biggest challenges of long-duration space missions. Because the ice is semi-transparent, natural sunlight can still enter the habitat, helping astronauts maintain healthy diurnal cycles and improving their overall well-being. Between the ice and the living area, there's a cellular carbon dioxide insulation layer that keeps the inside at a comfortable temperature. Inside, the habitat maintains an Earth-like atmosphere at 14.7 psi, consisting of 78% nitrogen, 21% oxygen, and 1% other gases, providing a safe and familiar environment for the crew. To increase self-sustainability, the habitat also includes a 20 square meter vertical hydroponic garden. Here, astronauts can grow crops such as bell peppers, cherry tomatoes, basil, dill, peanuts, dwarf peas, potatoes, and finally quinoa. Producing fresh food on Mars reduces the amount of supplies that must be launched from Earth, while also providing fresh vegetables for the crew. Next slide, please. Before entering the habitat, astronauts pass through a specialized airlock that also functions as a decontamination chamber. A HEPA vacuum system removes the toxic Martian dust from their spacesuits before they enter the living area, preventing contamination. Since every crew member has 2 spacesuits, one of them can also be accessed directly from inside the habitat through a quick entry suit port, allowing astronauts to prepare more quickly and safely for surface operations. Thank you.
You can hear me, right?
Yes.
Okay. We split the equipment to 2 launches since we are making 2 launches. The first launch will be unmanned, and we will send our habitat, 3 rovers, an emergency ATV, 3 nuclear reactors, which provides a cumulated energy output of 60 kilowatts, and other logistical items. As for the second launch, we will send our crew of 4 people. Alongside our crew, we will also send our food, a total of 8 suits, 2 per person, and our medical equipment. In our mission, we will use SpaceX's EVA suits. These suits are an advanced iteration of SpaceX's Crew Dragon intravehicular activity suits, also known as IVA. It features a greater mobility, NHUD, and thermal management textiles. Its key features are high mobility with articulated joints and improved patterns, a 3D helmet with a head-up display that projects suit pressure, temperature, and elapsed time, and lastly, it has a new thermal management textiles to protect astronauts. Also, the suit visor is coated in copper and indium tin oxide to block harsh solar glare. Thank you.
So the key to our long-term survival is our custom engineered ice mining rover, which is a vehicle designed to withstand the abrasive dust and cold of Arcadia Planitia. Each rover is built on a high-strength titanium aluminium alloy frame and rides on open mesh woven from nitinol. A shape memory alloy that deforms over jagged rocks to maximize traction and prevent punctures. To ensure these rovers can operate continuously to global dust storms, they are powered by a kilopower nuclear reactor. The reactor is safely isolated as the other three that we use to power the habitat. They are safely isolated from the vehicle's electronic base by a layered shield of lithium hydride and boron polyethylene. For the resource extraction, such as the ice, they use a carbide tip combined with a red water system to drill to the ice layer. Its total weight is about 1,200 kilograms. The chassis and avionics were around 400, mobility and wheels 200 kilograms, the red water system 170, LiDAR sensors and camera 50 kilograms, the nuclear reactor 150, and storage tanks 75 kilograms. We are also going to send the human transportation rover and ATV. The human transportation rover is based on the other rover, but instead of a red water system, it has a specialized pressurized it's pressurized, so the crew can drive it. It replaces, in case our human transportation rover is away on a mission or it doesn't work, we also send the ATV that is smaller and can hold two people without being pressurized.
Now I'll explain why we split the mission into two different launches. So our mission is divided into a cargo mission and a crew mission. This allows us to establish a functioning base before astronauts leave Earth. And the first launch carries all of the heavy infrastructure needed to support life on Mars. The largest component is the inflatable habitat, weighing approximately 12.5 tons. This will become the astronauts' home and includes living space, work areas, and environmental protection. The power is supplied by 3 NASA SR-1 nuclear fission reactors with a combined mass of around 3.4 tons. Solar power alone would not provide enough reliable energy because of Martian dust, storms, and the long nights, so the nuclear power ensures continuous electricity throughout the mission. We also transport 3 robotic rovers with a combined weight of 3.8 tons. These robots are responsible for preparing the base before the astronauts arrive. They deploy equipment, collect the water, ice, and perform maintenance tasks autonomously. An additional ATV weighing 600 kilograms will provide local transportation for the crew once they arrive on Mars. And to support long-term survival, we include the Environmental Control and Life Support System, or ECLSS, which maintains breathable air, controls humidity and temperature, and recycles the water.
You have, excuse me, you have 2 minutes to complete your presentation.
Okay. The first launch will also carry Sabatier reactor, fuel tanks, gas storage systems, power management, electronics, heat exchangers, and thermal isolation materials. Together, these systems allow the habitat to generate oxygen and recycle the resources. The second launch focuses entirely on supporting the astronauts themselves. It carries 4 crew members together with their personal equipment. To ensure food security throughout the mission, we transport approximately 2.2 tons of dehydrated food, including emergency reserves. Each astronaut receives 2 SpaceX Mars EVA suits, giving a total of 8 suits. Having spare suits increases reliability and provides backup in case maintenance or repairs are needed. The mission also includes 450 kilograms of medical equipment and pharmaceuticals. And for scientific research, we transport a deep core planetary drill, allowing samples to be collected from several meters beneath the Martian surface, where signs of ancient life are more likely to be preserved. 2 Mars Inequity helicopters provide aerial reconnaissance. They can scout future exploration routes, inspect difficult terrain, and identify scientifically interesting locations before astronauts travel there. And finally, we include a compact indoor science laboratory where samples collected during the mission can be analyzed. Overall, separating the equipment into 2 launches improves safety, reduces mission risk, and ensures that every critical system is fully operational before the astronauts arrive. This approach gives the crew the highest chance of completing a safe and successful long-duration mission on Mars. Thank you.
Thank you so much for the wonderful presentation. Is the next team here? I've put the names in the chat. If you are here, please unmute yourself and let me know. If the team is not here, we will take a break. So that team is scheduled to start in, oh, you're here. Okay, so let's take a break anyway and get to the normal start time so we don't get too ahead of ourselves. Let's start that presentation in 17 minutes. 17 minutes, so everybody take a break. I'll pause the recording and we will return in 17 minutes.
Can you see my screen?
It's popping up. Yes. Go ahead.
So, hello everyone. This is Team Sol Elpis with the project Terra Firma. This is our presentation. So, Project Terra Firma aims to establish the first permanent, self-sufficient industrial settlement on Mars by relying on local resources instead of Earth resupply. The settlement is powered by 2 Pylon 150 fission reactors, providing both electricity and waste heat for maximum efficiency. This energy supports ice mining, water electrolysis, methane production, a greenhouse, and protected underground shelter, producing water, oxygen, food, and rocket propellants directly on Mars. Finally, the mission is designed with redundancy. It remains within the 30-ton mass limit with an 8.8 contingency margin. And if the primary reactors are unavailable, a kilopower-based backup architecture can still achieve the mission objectives. This slide summarizes our key mission parameters. We selected a crew of 4 for efficiency and redundancy, with the 400 Sol surface mission focused on building permanent infrastructure. The landing site, Deuteronilus Mensaia, was chosen because of its abundant shallow subsurface ice. The entire mission fits within the 30-ton payload limit while maintaining an 8.8 contingency margin. 2 Pylon 150 reactors power the settlement, which includes a water-shielded habitat, a hydroponic greenhouse, and an underground emergency shelter. We also developed a complete backup mission using kilopower reactors if the primary power is unavailable.
So for the power system, our mission uses the Pylon 150 sodium-cooled fast fission reactors, which runs on high-assay, low-enriched uranium. Together, they have an electrical output of 300 kilowatts and a thermal output of 700 kilowatts. This allows us to have 520 kilowatts of waste heat available for other station operations. Together, the system has a mass of 9 tons, uh, which includes reactor cores, primary liquid metal loops, turbo machinery, heat rejection systems, and integrated shadow shielding. Regarding the placement, each nuclear reactor is placed 200 meters from the habitat on opposite ends, and automated utility rovers scrape local soil to construct massive regolith berms, providing a passive biological radiation barrier. And next slide. On the top right, you can see the power budget, and predominantly the electrolyzer takes a lot of power usage, which produces 33 kilograms of oxygen a day and 4.1 kilograms of hydrogen a day. The Sabatier methanation takes 15 kilowatts, and this produces 16 kilograms of methane for our fuel purposes. The water pumping and mining auxiliaries take 10 kilowatts. The greenhouse supplemental LEDs for the plants take 20 kilowatts. And for our science instruments and computing, they take 5. And the rover charging for the utility rover, they take only 3 kilowatts on average. On the bottom left, you can see the heat allocated from the waste heat from the nuclear reactors used for the crater ice melting, which is 300 kilowatts, using the 50 pipe sodium heat pipe array. And for the habitat and the greenhouse, each is allocated 50 kilowatts to have suitable temperature for the plants, and for the habitats, it's circulated through water jacket walls. 20 kilowatts for the underground shelter, and 100 kilowatts for the small deployable radiators. Total 520 kilowatts of heat is productively utilized. Yeah.
Okay, so water is one of the most important resources for a permanent settlement on Mars for drinking, growing food, making oxygen, and even rocket fuel. A system collects water from the ice buried below the Martian surface. For that, first we take a shallow crater through the top layer of soil until we reach the underground ice. Instead of carrying a whole separate heater, we will use the waste heat from the nuclear reactors. Around 3000 kilowatts of heat is then transferred through sodium-filled pipes. Sodium-filled heat pipes, which melts the ice directly where it is. The melted water collects at the bottom of the crater. A heated sump pump then pumps the water to the surface, so it does not freeze again. Before the water is stored or used, it passes through several filters to remove dust and other impurities. This gives us a continuous supply of clean water for the crew and every other important systems in a Martian base. Next slide, please. Thank you. This slide shows us how the entire water extraction system actually works. So, we dig a crater that is 6 meters wide and 2 meters deep using a 1.5-ton electric excavator. We leave about 30 centimeters of soil above the ice, which helps protect it and acts as the first layer of filtering. The main part of the system is an array of 50 vertical sodium heat pipes. Each pipe is 2.5 meters long and carries about 6 kilowatts of heat, giving a total of 300 kilowatts. A sodium to sodium heat exchanger transfers heat from the reactor to these pipes. As the ice melts, a heated submersible pump collects the water. The water is then cleaned in 4 stages. First, a mesh filter removes larger particles. Second, a centrifuge removes finer dust. Then reverse osmosis removes dissolved impurities, and at last, UVC light kills harmful microorganisms. The clean water is stored in a 2 cubic meter day tank for daily use, and a 20-ton storage tank, which can support the crew for over a year if water extraction stops. Next slide, please. Thank you. To make sure the design is practical, we perform the thermal analysis of the system. To check if a system is practical, we calculated how much ice it can melt. The underground ice on Mars is around minus 20 degrees Celsius. First, we need energy to warm it to 0 degrees, and then remove energy to melt it. In total, melting 1 kilogram of ice requires about 374 kilojoules of energy. With 300 kilowatts of waste heat from the reactors, the system can theoretically melt around 69,300 kilograms of ice per Martian day, also called a sol. After allowing for 20% heat loss, the actual capacity becomes around 55,400 kilograms per sol. However, our target is only 15,000 kilograms per sol. This means we are only using 27% of the system's maximum capacity, giving us a large safety margin if heat is lost or the equipment becomes less efficient. Finally, the extracted water isn't used to produce oxygen, methane fuel, and maintain a 20-ton emergency water reserve, making the system reliable for long-term missions on Mars. This makes our water extraction system simple, efficient, and reliable for supporting long-term human missions or even settlement on Mars. Thank you.
Next, I will discuss the living quarters and the life support infrastructure of our project Terra Firma. Our habitat architecture is designed for both maximum crew psychology and absolute safety, split into two main structures. First is our rigid core model. To meet our strict mass limits, we constructed this two-deck cylinder out of a lightweight aluminum lithium alloy, bringing its empty mass to just 3.5 tons. This core safely houses the crew's private cabins, the medical station, and the primary life support racks. But its most important feature is radiation shielding. We surround the core with a continuous water jacket that holds 13 tons of liquid water. We pump this water directly from our crater extraction system radiation without having to launch that heavy mass from the Earth. Attached to this core is a 50 square meter inflatable dome. We used a layer composite of Vectron aerogel and ETFE fabric. This gives the crew a large, highly insulated common area and kitchen that only adds 1.5 tons to our payload. Finally, every material in both structures strictly complies with NASA STD 6001B flammability standards. We integrated automatic CO2 and water mist fire suppression systems. The greenhouse. Second slide, please. The next slide, please. The greenhouse. Moving on to our agricultural system, we are not just bringing fruit, we are growing it. We deployed 6 modular hydroponic racks on wheels, providing 150 square meters of growing canopy inside a surface inflatable shell. By utilizing both natural sunlight and reactor-powered LEDs and heating the greenhouse with reactor waste heat, we maintain a stable 15 to 25 degrees Celsius environment. This system yields roughly 1,800 kilocalories per day, covering 25% of the crew's dietary needs with fresh crops like sweet potatoes, soybeans, and tomatoes. Crucially, because these racks are on wheels, they serve as a backup life support system. In an emergency, we can physically roll them to our underground shelter to provide supplemental oxygen and carbon dioxide scrubbing. Next slide. Underground shelter. That brings us to our most critical safety feature, the underground shelter. We utilize a rover-powered electric auger of 1.2 diameter and 0.5 tons to bore a 3-meter deep shaft directly into the ice-cemented regolith. At the bottom of this shaft, we deploy a 2.5-meter diameter inflatable chamber weighing 0.2 tons. This location provides incredible safety as 3 meters of Martian dirt and ice provides 450 grams per square centimeter of radiation shielding. This completely neutralizes the threat of solar particles events and allows the crew to occupy the shelter indefinitely from a radiation perspective. We line the shaft with reflective mylar and capped it with polycarbonate skylight to pipe natural sunlight down to the chamber. Between the 20 kilowatts of thermal heating routed from our reactors and the ability to lower our greenhouse racks down the shaft, this shelter guarantees crew survival even more in our worst case failure scenarios. Moving on to the next speaker.
If someone's talking, we can't hear you, so let us know if you're there.
Okay, I'll say them. So the utility rover has a mass of 0.6 tons and features an operational range of 80 kilometers. It is capable of carrying a payload of up to 200 kilograms. This vehicle is unpressurized, electric powered, and designed for local transport and light excavation tasks. Additionally, it is equipped with an auger power supply. And the Nomad 1 rover has a mass of 4 tons and is built for long-range operations, offering a travel range of 500 kilometers. Its payload capacity supports a crew of 2 for up to 7 days. This is a fully pressurized long-range rover that is integrated into the Nomad station specifications. The science program. The 500 kilogram science payload addresses 4 primary hypotheses at Deuteroneus Mensah. The sample curation follows COSPAR category IVB protocols. The crater melt water pool, once established, provides a unique direct access window to subsurface liquid water, not available to any other proposed Mars mission. So here are 4 domains in which we're going to explore Mars. First is past habitability. The hypothesis is that ancient river channel sediments contain organic biosignatures from Hesperian habitability. Second is climate history. Glacial ice records obliquity-driven dust and volatile cycles over the Amazonian epoch. Third is ice-atmosphere interactions. Seasonal frost deposition and sublimation at 4C degrees north are measurable on diurnal timescales. Fourth is deep surface life, astrobiology again. The meltwater pool beneath the crater may harbor hemolithotrophic microorganisms. And on the right, you can see the instrument that we use to explore this. The mass budget of our project. All individual subsystem masses include internal margins of 10 to 20%. The 8.83% contingency margin provides a robust buffer against mass growth during detailed design. All masses independently verified. Sum closes exactly at 30 tons. So the heaviest item is 2 Pylon 150 reactors. Then our habitat system, which is core plus dome. Third is crater mining equipment, 2.5 tons. Water processing and storage, and so on, as you can see. The subtotal mission hardware sums to 27.35 tons, with a contingency margin of 2.65 tons, which adds up to 30 tons.
Until this point, we have demonstrated the functioning of terra firma under normal circumstances. Nevertheless, space-based systems do not operate under optimal conditions. They operate under the assumption of malfunction instead. That is why all vital systems on terra firma have a backup route. For example, in case of a power plant failure, our backup batteries and methane fuel cells sustain life support processes while repairs take place. In case of a compromise of the surface habitat, our astronauts can move to the underground bunker where they will have their own systems of heating, lighting, and environmental control. Moreover, in case of problems with water harvesting, our reserve of crew water supply allows them to survive during a whole year. And in case of failure of greenhouses, our food supply sustains the mission for its entire duration. In any case, none of these scenarios system failure leads to loss of crew or loss of mission. While terra firma, next slide. Next slide. While terra firma is based on the Pylon 150, wait, the one before. Yeah. While terra firma is based on the Pylon 150 reactor architecture, we understood that advanced fission reactors might suffer from technology and program risks. We created a wholly different and independent contingency mission known as the Nomad Station. This station uses 4 flight-capable kilopower 10 reactors and a long-range pressurized rover system to replace the industrial pylons. The mission no longer emphasizes industrial-scale extraction, but rather long-range exploration and science. Most importantly, the new architecture still stays within the same 30-ton mass and does not require any revolutionary technologies. To summarize, terra firma does not rely on one reactor system or one technological breakthrough. Next. Project Terra Firma is an industrial-scale colony on Mars designed from scratch. 2 Pylon 150 power generators provide 300 kilowatts of electrical energy and more than 500 kilowatts of waste heat for use in water recovery, oxygen production, methane manufacturing, agricultural activities, and sustainable living. Our mission fits entirely within the allowed weight limit set by the competition at 30 tons, while keeping an 8.83% contingency margin, as well as providing backup solutions to every critical system. Either via the main terra firma mission or the Nomad Station contingency route, our mission is protected against possible engineering and technology immaturity risks. Terra firma does not rely on any specific technology, and it is an industrially robust architecture for a colony on Mars. Thank you.
Thank you for your attention.
Thank you.
Thank you so much for the wonderful presentation. The next presentation will start in 5 minutes. Please stand by.
Hi, I'm Hadi Harfoush from the Dex Lab 1 team, and I'm going to share my screen while my teammates talk about their specific thoughts. Is my screen showing?
It's coming up. Just give it a second. There it is.
Yeah. Humam, you're up.
If someone's talking, we can't hear them.
Humam, it's your turn.
Okay. Hello, everyone. Team DexLab1 here. Good afternoon. We are Team DexLab1, and we have our mission to Mars, which called Dragon Iris. Wait. Just a second, please. Okay. To the next slide, please. This is our team: Fatima Al-Sadi, Humam Mariam, Tala Muhammad, and Hadi Harfoush. Mentored by Dr. Basir Sultan and Dr. Hana Raslan. Between us, we cover engineering, science, and mission design, which is exactly how a real mission team is built. Our vision to establish a scalable, sustainable, and scientifically productive human settlement on Mars, we get there by integrating 4 things: advanced engineering, autonomous robotics, in situ resource utilization, and long-term life support technology. Every subsystem we'll show you today is back to one of those 4 pillars. Dragon Iris is a long-duration Mars settlement. A long-duration Mars settlement mission designed to establish a sustainable human presence on the Martian surface. It combines advanced robotics, ISRU technologies, autonomous constructions, nuclear energy systems, and agricultural self-sufficiency. The project runs in 2 main phases: robotic preparation and construction. First, the human settlement and colony activation. Here is what we'll cover on the science side: our 2035 launch window, our scientific objectives and methodology, how we selected our landing site and colony location, and the geological analysis via remote sensing that backs it all up. Mars launch windows repeat roughly every synodic period, about 780 days or 25.6 months. Starting from 2026, they land in 2028 or probably 2028 or 2029. 2031, 2031, 2033, and 2035. We chose 2035 specifically because it's the first window that falls after the international missions Escapade, Rosalind Franklin, and Tianwen-3 have already returned their science, which we can fold into our own models without ever depending on them operationally.
The launch window is explained as the following.
This is what that window actually looks like. Earth and Mars in their orbits with with the transfer trajectory linking them at the point they're closest and most energy efficient to bridge. Our robotic payload take the economical Hongman transfer, roughly 7 to 9 months, and the crew launched later in the same window, so they arrive right as Phase 1 wraps up, which will be explained later. We've organized the mission into 6 objectives across 2 phases. 1. Establish a permanent human settlement. 2. Demonstrate sustainable resource utilization. 3. Validate autonomous robotic construction. 4. Support long-duration scientific exploration. 5. Reduce dependence on Earth resupply. 6. Develop a scalable model for future Mars colonies. Notice that only the first 4 are about getting to Mars and surviving. The last 2 are about proving the design could be repeated. To the next team member, Tala, please continue. Thank you for your time. I finished my...
Hi everyone, I am Tala. And this is our mission architecture, end-to-end. Earth, launch vehicles, transfer vehicles, Mars orbit, infrastructure, human carrier arrival, and finally, an operational Mars colony. One continuous system intervening transportation, robotic energy, and human opportunity. And the second slide. Here is the Janet chart trying it together. First one runs September 235 to January the next year. Water extraction, gas production, HDPE production, iron extraction and processing, then printing, and only construction in that order. Because the reactor can't pour all of it once. Phase 2 runs to rest of 236 final touches in this. And the next slide, this is the exact spot, Doe Village, roughly 8 degrees south east. On the left, close ring HRSC and MOLA. Data show the terrain near the mouth of the valley. The next slide, it's zooming in the future. This is the valley itself. The area mark that ancient direction water covered this channel, and the outland zone is the specific commodity set we ground treated against the slope and data. On the right, a digital thermal model of the same corridor show the redundancy a heavy rover needs to avoid. The next slide, their numbers explain to the shows. Doe Village has a highest atmosphere pressure anywhere on Mars, about 100 pascals average, against a global average of 60-10. The next slide, on the energy slide, in the engineering side, sorry, our overall mass budget, energy and consumption budget, the Mars Lighthouse navigation system, our robotic fleet and aerial platform production lanes, and Earth swap. And I am finished. Please, my next friend Hadi complete. Thank you, and I am sorry for my bad accent.
Don't apologize.
Uh,
Your accent's beautiful.
Yes, thank you. The following tables show the exact coordinates we're aiming for in the landing location. As shown, we have the specific locations with the distance, the evidence, and all the orbital data we need. This is a comparison between the Hellas Planitia region, which is where the landing site is, and the zero crater, the Valley Marianus. As shown in the table, we can suggest and confidently say that Hellas Planitia has the highest atmospheric pressure and the easiest to consume in-size resource utilization. This is a following table showing the data that we had, further data that we had. The engineering overview. I'm gonna have to stop just for a moment because I'm having another tab for what I'm reading and I couldn't just share it, so 1 second.
Is that the end of your presentation? No, okay.
No, we have a lot coming, but I have another slide,
Oh,
another
okay.
tab for the information, and I'm just figuring out how I'm gonna have the both of them on the screen. Is everything showing?
It's getting ready to. Yeah, there.
Yes. So you're saying the engineering overview.
I see the engineering.
Yes, okay. Our engineering overview is as following. First, we have the overall mass budget, the energy and consumption budget, the navigation system, the robotic fleet, the production line, and in-size resource utilization, the 3D printed colony, the mass integration, and then the human waste management in the human section. Here is a chart showing the pie chart and the table of all our weights, founding just at a 30-ton radius with a margin. Notes. As it's noted, the largest single item we have are the reactor, the two production lines, which are collectively 16 tons, more than 50% of the mass budget, which makes them the top priority for any future mass optimization and the easiest to and since they have a long lifetime expectancy, the next crew won't have to get them. Here is our energy system. I'm sorry. Yes, I'm gonna continue like this. I'm sorry for that inconvenience. The energy system is the Equilor reactor, following at 1.5 megawatts of electrical capacity, 4 megawatts of thermal capacity, just over 5 tons of mass. This and he have passive cooling, operational lifetime of up to 20 years without refueling, with the possibility of refueling with solid state batteries with 500 kilowatts per kilogram of density. with a TRL approximately 7 technological maturity based on testing in the International Space Station in the 2021 and 22. Here is a table and a pie chart showing our full energy budget and consumption. As shown in the table and the pie chart, the peak of our consumption won't exceed, at the maximum circumstances, a 984 kilowatt, which is only 65% of the reactor's total electrical capacity, with a safety margin of 34.4%. And the conversation mode only takes 284 kilowatts, well below the capacity limit, allowing for any other activity. Yeah, if you have a way, I'm having another tab. I'm reading from another tab, but it keeps disappearing. I'm so sorry. Do you have any idea over?
4 minutes. 4 minutes.
You can share it with a teammate and maybe they can share the screen. Do they have a copy?
Yes, Fatima, can you share the screen, please?
Can't find it.
There's a button at the last of the corner. On the bottom of the screen, there is a share, a box and arrow.
If you can't find it, I can share my screen.
Human, is everything okay? Can you share your screen now?
Can you find it?
Okay. We're gonna continue on my screen.
True.
As in the diagram, our mission is practically following the Insights Resource Utilization Program. The local Martian resources are being used for water extraction, oxygen production, hydrogen generation, oil processing, HDPE manufacturing, and 3D printing construction. As shown, using local Martian resources reduces the dependency on resupply for long duration missions and sustainability. As shown in the second paragraph and the second graph, we have a closed cycle, meaning each and every consumable will be redirected and won't be wasted. The Colony construction process is 2 phases. The water extraction, the first one is 9 months robotics. It's an non-human mission with water extraction, production, and production of oxygen and hydrogen gases, and HDPE production, the iron extraction and processing, production of the finished iron, printing and building the colony. The phase 2 is a 9 month of human operations. We're gonna have the permanent settlement. There will be supervision for and inspection of the final touches of the 3D printed habitat, and there will be a transition of agriculture into a part self-sufficient food. The robotic fleet overview. Each element of the following will be presented as identity, function, development, and connections. As I'm having some problems with the slides, I'm sorry if I forgot any part, but I'm gonna try to remember everything. The common platform. It's practically developed of the MMSCV NASA rover with the following modifications. Magnetic brake system, which will help in the rigid terrain, an air-free and maintenance-free nylon metal tire, and an expandable telescopic structure to avoid any obstacles or to ease terrain navigation. It's also the main operational standards for all the rovers. So everything following will be mounted on this common platform. Then we have the 3D printed rover. The identity is a Kokark Quantic commercial robotic arm at the base. The foundation is a printed metal head frame and an HDBE panel for the colony. The developments are as following, and I'm sorry if I forgot any. Magnetic induction metal print head, laser print head for error correction, an EAM print head for HDBE print head will also be installed with an either CAT or ROS protocol control for motion modeling using inverse kinematic libraries. The connection. This rover will be basically connected with the HDBE and iron production lines and with the helicopter, with the Mars helicopter for accommodation and for live quality monitoring during the printing process. The drilling rover. The extraction rover is designed to extract ice from up to 20 meters in the Martian soil. The dual drilling system, Helica ultrasonic, focused microwave chemical process unit, and GPR SAB radar for ice layer identification. An important engineering note we have, I'm searching for it, 1 second.
The crew.
Yes, 1 second.
I believe the next team is here. So if you could, I know you're having technical difficulties and it is not your fault. I understand. So if you could wrap it up in the next 2 minutes and prepare for the next team.
Yes, okay. So I'm gonna have to cut on everything that we're gonna speak. I'm gonna just say the headlines. A previous version, a previous rover on the Mars couldn't reach 2 meters because the Martian soil doesn't have enough friction for it. So we modified ours to have ultrasonic and multiple ways of drilling. So it's basically more like a Martian oil drill than an actual drill head. The tank rover is going to have all the water and gases transports. It's going to have a 200-liter water tank and a metal solid transportation tank with a pump and a soil ejector for soil. The function is to transport all the extracted water and iron gypsum materials from the drilling site and the central processing unit. She will be basically connected with all the production lines and the 3D printed rover, the 3D printer rover. The power rover is going to have a 10 kilowatt clip power system in case for an emergency with a Okola reactor, and for extra power for all the rovers in case any of them ran out of battery or needed a higher power consumption rate. The rigid quadrupeds are developed from commercially available units and will be used for commitment on the landing sites and all the operational sites. In other words, before any heavy rovers are moved, rigid quadruples, 4 of each, 15 kilogram, are going to be moved to the location to make sure that the resources are existent and the land is rigid enough for all the heavy rovers so we have no mechanical casualties. The Halo SWAC helicopter. Disclaimer, the photo in the slide does not represent the final helicopter. The radical development of the Ingenuity model with eight routes distinct across four pairs instead of two. It will have constant surveillance, mapping, and stealth-light paths, carrying a thermal imaging camera and a GPS, with improved flight time of 70% to 120% and payload of 30% to 50% because of the higher air pressure in the landing location. The connection will be operational with all the rovers, especially the 3D printed rover, to make sure no miscuts will happen. According to the following calculations, we calculated the solar balloon. I'm sorry, I'm gonna have to cut through this part. This is an area of the solar balloon and a quick table between the helicopter and the solar balloon. The human operations. Fatima, you can take this part if we have enough time.
The crew consists of 6 astronauts with different civilizations working together as one team. The astrobiologist, the space system engineer, the aerospace mechanical engineer, the space robotic engineer, the space medicine physical. And finally, the mission commander leads the crew and manages all missions, operation, and critical decisions. Our search explanation, we used a modified version of NASA's XEMU suit, designing at receipt Martian dust, radiation, and extreme temperature. In conclusion, Dragon's area combines advanced engineering, robotic and AI, resources utilization, scientific exploration to support long-term human survey on Mars. Thank you for listening, and we are ready for your questions and feedbacks.
Thank you so very much. Wonderful job. Even with the technical difficulties, you did a great job. Okay, next team. We are ready for you to present. Make
Yes.
sure you introduce yourself and your team. We can see your screen, but can't hear you yet.
Okay. Hello, everyone, and welcome to our technical briefing today. I am proud to presentation DXLab 2. I Layan Munajed from DXLab 2 team. Good morning, everyone, and welcome to our technical briefing today. I am proud to presentation DXLab 2 mission to Mars 2026. This presentation will involve our highly detailed architecture and engineering framework designed to transition humanity from low Earth over exploration to long duration planetary habitation. Over the next 20 missions, we will break down the precise technical protocols all govern or giving mission to G0 creator, proving that human life be sustainable and safely on the red planet. Thank you for you. I will going to play the video. Sorry, but the internet in Syria is so slow.
For sake of time, you may want to skip the video if it's going to take a long time.
Okay, moving to slide 2, let us establish our code original. Sorry, I am closing the camera because internet very slow. Moving to slide 2, let us establish our code operational timeline and strategy alignment. The absolute foundation of this mission is the 18-minute servers residency protocol. This duration is not at choice. It is strictly dictated by orbital mechanics. The island windows between Earth and Mars only open every 26 minutes. Therefore, once our crew lands, they must remain on the server for exactly 18 minutes before the planets realign to prompt a fuel-efficient return trajectory. Free system we this today is engineering to withstand this rigorous discharge, full aligned with the NASA deep space exploration pathways. Our primary objective bridge the gap between engineering survival and ground-bearing science. First, we must achieve structure autonomy by constructing a habitat that functions continuously without real-time response from Earth. Scientifically, our focus is topology and geology. We will conduct deep servers if ancient mudstone formations to search for fossilized microbial biosciences. Most critically, we will state into resource utilization our ASRU to extract water and synthesize fuel locally. Finally, we are utilizing isotopes mammalian research modules to study how Martian gravity, which is only 38% of Earth's affect biology system over long durations, demonstrating the technologies required for future permanent clones. Why did you choose G0 Creator? It is located at this exact coordinates. This site contains a perfectly preserved ancient river delta. Our primary goal here is to find subsurface water ice in narrow layers. Scientifically, it has high clay and carbonate content. To preserve organic materials, most importantly, the flat terrain ensures a safe landing and automatic construction. To achieve our science goals, we use two advanced instruments. First, the Orbital Spectrometer. It provides high-precision organic analysis to detect amino acids at the BBP level. Second, the ground bearing radar or GBR. This instrument scanners the ground laser to map subsurface water ice, completely implementing the need for random relaying. For shelter, we chose the hypermodular design. It is the best engineering architecture for the harsh Martian environment. The habitat features a 3-layer shell system. The outer layer is 3D printed regular shell to protect against radiation. The mid layer is a refiner still. Structure for interior air pressure is the inner layer is a HDB in E liner to block secondary cosmetic rise. Power is critical for baseline energy. We generate 40 kilowatts consecutive using kilopower nickel writers. The ensure our piece works perfectly even during blast storms. For daytime power burst, we use flexible slave kindling solar arrays. To keep them efficient is this technology, automatic removing that using microelectronics.
Are you still there? Because we can't.
Yes, yes.
Okay.
Yes, I am here.
Go ahead. Go.
This is kilopower.
Is everything okay?
Yes, yes, I am here. Environment control and life support system ESLS continuous regulation atmosphere communication temperature humidity and capping pressures closed loop resealing system rovers approximately of metabolic moisture and water automated atmosphere monitoring continuously adjust oxygen and nitrogen concentration. When our astronauts exploring the server, the wear's advanced IFS, it has a multi-layer thermal shield protecting against extreme temperatures from -122 plus 120 degrees. The PLSS pack provides continuous oxygen and mechanically removes the out. It also tracks biometrics like heart rate, blood pressure, and radiation in real time. Successful mission requires cross-training. Our crew consists of 4 main operational roles: the mission commander specializes system engineering, the mission physician focuses on space medicine and physiology, the ARSRU chemist manages
atmospheric processing, and the power engineering offers nuclear reactors. Everyone is cross-trained to pack Earth up perfectly.
We can't hear anything.
How is day structured on Mars? Our 24-hour Mars Sol operational cycle is highly detailed. It requires 8.0 hours for Matador in Intrepid, rest in acoustic isolation. Cabin 7.0 hours are dedicated to scientific fieldwork and exploration. 3.0 hours are spent on intensive physical or countermeasure training to preserve bone density, followed by group nutrition, metal deconnection, and system maintenance. Our final technical slide details our human capital. The mission utilizes highly specialized 6-member multi-discipline and collagen. The engineering parameters: hybrid power jets, closed loop recycling, noters, and atmosphere framework of DixLab 2 are the foundational building blocks. Of DixLab 2, the foundational building blocks required to transform humanity into a multi-planter speech. The six of these intent residents at Zero Creator will be the why for permanent thriving human civilization on Mars. Thank you very much for your time and attention. I will now open the floor to technical or personal concept you might have regarding the mission. Thank you for listening.
Thank you so very much. If there are any questions, we can put them in the chat. Is the next team available? I believe it's DexLab 3. Are you here?
Yes, just 1 second.
Okay, you have 5 minutes before your start time, so take your time and get ready. And we will start in 5 minutes. So everybody take a stretch break.
Okay. Okay, can I start?
No, let's wait 5 minutes. I will announce when we start, okay?
Okay.
5 minutes. You may begin your presentation. You have 20 minutes. If you are speaking, you are muted.
Okay, I'm sorry. Okay. Hello everyone, I'm Jenna Omar from Egypt and from Team Dex Lab 3. And then I will show you our mission, which is called STEMA. These are all these topics that we are gonna discuss in this presentation together with you. First of all, the most important question is what is the purpose of our mission? Honestly, our primary goal is to find any signs of past of current life. We are trying to design a closed loop system on Mars, essentially a self-sustaining environment like Earth. That's why we designed our mission with 4 astronauts to stay there for 18 months to answer and satisfy our curiosity on these 4 main points. Was there ever a life before Mars, and does it still exist? Can humans ever live long term on Mars for 18 months? Can we make use of the resources on Mars? Is really drinkable water there? Can someone survive just with this water? Okay, let's move on the first part, which is the landing site. We found the most suitable place for gold, which is Amazonas Planitia. It's located in between volcanic provinces Tharsis in the east and Elysium in the west. We chose it especially because it's the closest to the Martian equator perth water ice has ever been found. There is evidence it could be just 1 meter under the surface, and it's warmer and safer to land. And this ice would be a critical resource for astronauts as drinking water, for agriculture, and for rocket propellant. And since there is the ice, there would also be signs of past of even current life on Mars. For all these reasons, and with its flat surface, we choose it to achieve the goals we wanna verify. Okay, the next section is habitat. The Martian colony is established after landing using surface ice as a source of water and transparent radiation shield with a thickness of 1.5 to 2 meters that reduce radiation by about 50%, while allowing natural light to enter. With the with the use of soil locally in the production of sulfuric concert heated by 120 to 150 diagram and centrated prick to 1,200 to 1,500 diagram with a strength of 30 to 60 MPa and an age exceeding 50 years. In addition to a self-growing biomaterial from the symbiosis of blue algae to absorb CO2 and nitrogen and production of oxygen, organic substances and filamentous fungi to pen the soil and from mineral crystals, with the possibility of strengthening them with carbon tubes of 7% by weight and pressed at 70 diagram to give a compressive strength of up to 100 MPa, electrical conductivity, and piezoelectric response. The construction is carried out with a three-dimensional printer with a spiral design that increases structural rigidity and reduces heat loss, and includes 3 wings. Okay. Residential glass rooms and a kitchen, research with laboratories and control room and communication and a service with an airlock, equipment and environmental control with the integration of aerogel layers and variable phase materials (PCM) to absorb heat by day and release it at night. Multi-layer composite pressure crusts reduce mass by 30 to 40%, and silver pairing membranes containing water cells that freeze when leaking. Integrated dust control system during lotus effect self-cleaning, electrostatic lessons with efficiency 19 and 50%, HEPA filters provide 99.97% of 0-point micrometer particles, nanofoam save 40% in energy consumption, advanced atmospheric control 90 and 8% efficient CO2 removal using zeolites and O2 generation by electrolysis of water and a rate of 0.84 kilogram per person per day with improved efficiency 15 to 20%. Intelligent distribute sensor for monitoring and remote control with every warning of leaks and contaminates isolation of its used 252 tons of Mars, only 10 tons of Earth. It's incredible, and a total construction capacity of 50,000 of kilowatt, while the daily operation consumption is 45 kilowatt per hour. Using the selection nuclear reactions, construction is completed within 4 to 6 weeks, leaving a large surplus of capacity, becoming an integrated design to achieve sustainable human settlement on Mars. Okay, the next section is about robots. We use AALS Explorer robot. It's the ideal tool for us, especially when it's targeting the Amazonas planitia region. It's characterized by its weight, which is 100 kilograms, and it's characterized by autonomy and artificial intelligence, as it relies on 4 pairs of stereoscopic cameras and a lidar system. Navigation algorithm use an integrated library of movement patterns such as side sliding, still turning like a banana, for risk assessment and safe route selection, with a built-in ability to recover from mechanical failures. And the second one is the Lassie project. The Lassie project is based on robotic platforms with leg, where the leg monitors themselves are used as sensitive sensors to measure the properties of frozen and solid soil during movement. The system converts the robot's movement into an instant scientific survey tools without the need to wait for human intervention for the ground. Okay, there are 2 videos about them. Sorry. Okay, it's about Lassie. Okay, who will complete our presentation with you is my friend Rana. Okay, it's your turn.
This mission requires a lot of movement to explore Mars, so choosing the correct spacesuit is important. We choose the Z2 model spacesuit It allows flexibility, and since the whole weight is on the shoulders, they have natural movement at the bottom that allows climbing, descending, entering crates. It also has shoes for protection from falls. For this mission, we choose the Space Exploration Vehicle, in short SEV. The SEV would have the pressurized cabin on a flying platform that allows astronauts to live inside for up to 14 days. It has a weight of 3 tons, can walk up to 200 kilometers at the speed of 10 kilometers per hour. Since this mission is a 4-astronaut mission, we plan to bring 2 SEV rovers to allow the flexibility of exploring 2 places at the same time. For the tools, to be able to actually explore Mars, we need a few tools to help us. First is GBR, short for Ground Penetrating Radar. It will be used to study the Martian layers of up to 20 meters, very useful to understand the development of the planet. Second tool we have planned to bring is PIXI. It is very precise to measure the makeup of rocks and regolith at the very tiny scale. Third tool is the Raman spectroscopy. It is very useful for this mission goals since it can detect minerals and detect water, which is a big indicator for life. And sustainability is very important for every single civilization ever, because it allows them to have a sturdy supply of everyday essentials like water, oxygen, and food. So the first step to have a sustainable Mars colony is producing our own oxygen. But how? As you all know, Mars has a ton of carbon dioxide. The Martian atmosphere is around 90-55% carbon dioxide. We can make use of that. We will use this machine called ISRU plant. It takes carbon dioxide from the air and turn it into oxygen. Carbon monoxide is toxic for humans, so we decided to make use of it. We feed it to the Sepastia reactor with hydrogen, which gives us water and methane as fuel. But how are we going to get hydrogen? We will use the MHD electrolytic cell that takes in water we got from the Sepastia reactor, separate it into hydrogen and oxygen, so now we have more oxygen, also methane for fuel. We are going to produce our own water from the Martian regolith. So the regolith is 3% water, so we are going to use the Regolith Advanced Surface Operation robots to mine large quantities of the regolith, then feed the regolith to the MISWE that collects water from the regolith with an efficiency of 92%. So in 1 ton of regolith, it gives us 27 kilograms of water. Then from here, my teammate Mariam is going to continue.
Our food production system utilizes the colony's water recovery system and a controlled environment agriculture system, which enables crop production in a closed greenhouse. The crops are grown inside a rigid pressurized greenhouse with a cylindrical geometry due to its high tolerance to internal pressure difference. It also provides sufficient vertical space for the multi-tiered hydroponic system, which allows to maximize food production within a limited greenhouse volume. Crops were selected based on NASA's nutritional recommendations. We provided our greenhouse with several technologies to maintain the ideal growing environment. The first is an ISRU-based solar concentrator system, which provides the greenhouse with the electricity needs. Instead of relying entirely on the stored electricity, the system collects and concentrates sunlight, then it is transmitted to the greenhouse to illuminate the crops, and the rest of the concentrated sunlight is converted to electricity that generates up to 15 kilowatts to provide the greenhouse with the rest of the electricity needs. As shown in the figure, the system includes 2 photovoltaic arrays, each with a diameter of 5.4 meters, generating 7.5 kilowatts of electricity for a total of 15 kilowatts. Below them are 2 solar concentrator arrays, each with a diameter of 6.64 meters, which collect and concentrate solar radiation. The images on the right show the concentrator faces that focus sunlight into optical waveguides. These optical fibers transport the concentrated sunlight with minimal losses before interface optics distribute it throughout the greenhouse for proper illumination. The greenhouse is also equipped with an intelligent controller that continuously regulates temperature, humidity, carbon dioxide concentration, nutrient solution, and light intensity and spectrum to maintain the optimal environment for plant growth. Lighting was also optimized to maximize production efficiency. NASA compared different red and blue light combinations while growing Mizuna vegetable in the International Space Station. Although multiple light spectra produced high fresh mass, 90% light and 10% blue spectrum was selected because it generated greater biomass and higher yield. Rather than using a single cultivation method,
The greenhouse is provided with multiple hydroponic systems chosen based on the crop needs. The nutrient film technique was chosen for shallow leafy crops because it provides efficient nutrient delivery while using very little water. The deep water culture supports plants that need continuous root submersion in water. The media-based hydroponics provides the structural support needed for deep-rooted plants. To minimize the required area while maximizing crop production, the number of tiers for each plant was selected based on crop canopy height, the optimal lead to canopy distance, which is 15 centimeters, and the dimensions of the hydroponic systems. Okay, my friend Ham, we'll continue with you. Ham, it's your turn.
Hi, I'm here from Dix Lab 3 and I will talk about astronauts' needs. Human factors in this combination is very important. It's what keeps astronauts motivated and applied to continue in this harsh environment. So, what does astronauts need on daily basis? First, they need oxygen. It's the most important element for breathing, and each astronaut needs around 1 kilogram of it per day. Second things they need is water. It makes up around 60% of body weight, and it helps the body cool and moisturize it. One astronaut needs around 3 liters per day. Third, it's carbon dioxide, which is word isn't bad for humans, but actually is very important. It's help regulate both pH level and also stimulate breathing. Astronauts problems. Astronauts face many difficulties and they leave everything behind and go to completely new plant for the sake of science. They can face a lot of problems in Mars, such as sleep problems because of change in day and night cycle. The solution for this is to have artificial light in the habitat to regulate their sleep. And this is our presentation. Special thanks to my team, Rana, Jana, and Mariam. Thank you for listening.
Thank you.
Thank you so much. We have several minutes before the next presentation. Is the next team here?
Yes.
Yes. Yeah.
Okay, perfect. We will start in 9 minutes. Everybody take a stretch break. I know it's been a long day and we have several more hours to go. So take a break, get a snack, and we'll be back in 9 minutes for the next team. Go ahead.
All right.
Welcome to Mission Alethea, made by Team Red Frontier. Our mission, Alethea, is a two-phase mission to Oxia Planum to find signs of extinct life, current geology, and to conduct experiments that help us know whether the planet is habitable for humans.
So here's kind of like the timeline of our mission. So it's there's two kind of like phases. One is like the cargo mission where like I know no there's so the cargo is kind of set up before the humans, right? Abel?
Yeah, It is 2 missions designed to carry the cargo first and then humans to Mars on an 18-month mission. So, I'll hand it over to you now, Aditya.
All right, so our chosen site is Oxia Planum, which is this broad, relatively flat plain of land known to preserve some of the oldest exposed rocks on the Martian surface. Now, these rocks date back all the way to the Noachian period, about 4 billion years ago or so, which is around the time that life originated on Earth. And this was a period in which on Mars it was a lot warmer and wetter, much akin to that of Earth. So, which is why scientists believe that if life ever originated on Mars, it would have been during this time period. Okay, so now observations from ESA have identified extensive clay-rich deposits which form in the presence of water and are excellent at preserving organic molecules and potential biosignatures. The site also contains exposed ancient bedrock, allowing us to study Mars' early geological history without any kind of like extensive excavation. And it's also the chosen landing site of ESA's Rosalind Franklin mission, which just kind of it was somewhat of an indicator for us that this is like a safe enough landing site for our mission as well. So our mission combines both autonomous robotic exploration with actual astronaut-led field science to investigate the geological history of our landing site. So our research is organized into 5 main objectives, which is the main one being detecting ancient biosignatures, reconstructing Mars's geological evolution, assessing ancient habitable environments, demonstrating in situ research utilization technologies, and evaluating a closed-loop algae bioreactor to support long-duration future Mars missions. So, yeah, the absolute highest priority objective is the search for ancient life. Okay. Once again, as I said previously, we focus on this site because it contains some of the oldest exposed rocks on Mars, and therefore has some like kind of pristine, untouched evidence of life that you wouldn't find somewhere else. So our investigation will look for chemical, mineralogical, and structural biosignatures that could indicate any kind of past microbial activity. We will also analyze organic compounds preserved within clay-rich sediments, as these minerals can protect potential biosignatures from radiation and oxidation over billions of years. So our second objective is to reconstruct the geological evolution of Oxia Planum and understand how its environment changed over billions of years. We will investigate sedimentary stratigraphy, ancient river deposits, and clay-rich environments to determine how water shaped the region during the Noachian period. Using the Frontier rover's PanCam stereo imaging system, ground-penetrating radar, and a 2-meter rotary percussive drill, will examine subsurface rock layers that have been protected from radiation and surface weathering. Samples collected by both the rover and astronauts will be analyzed using Raman spectroscopy, X-ray fluorescence, and mineralogical analysis to identify changes in rock composition and past aqueous processes. Now, our third objective is to assess whether or not this site once contained conditions suitable for life. We will investigate evidence of long-duration liquid water, as stable water is one of the key requirements for habitability. We'll also study the formation and distribution of clay minerals, which develop through prolonged interaction between rock and water and can preserve evidence of ancient environments. By analyzing the site's redox chemistry and pH conditions, we will determine whether Oxia Planum could have supported microbial ecosystems. Finally, we'll investigate environments capable of preserving organic compounds and potential biosignatures, helping us identify the locations most likely to retain evidence of ancient Martian life. Our fourth objective is to demonstrate ISRU technologies by producing essential resources directly from the Martian environment. So throughout the mission, the crew will routinely monitor atmospheric carbon dioxide and evaluate how efficiently it can be converted into oxygen, building on NASA's MOXIE technology demonstrated on the Perseverance rover. We'll also investigate regolith composition to identify materials suitable for construction and future resource extraction. Water recovery systems will continuously recycle wastewater, while plant growth experiments will measure how effectively locally produced resources can support food production. And now our final experiment is to evaluate a closed-loop algae bioreactor as a sustainable life support technology for future Mars missions. This is something that kind of sets us apart in a lot of ways. So unlike conventional life support systems, this is a long duration experiment that investigates whether algae can continuously recycle crew waste into useful resources. During the mission, we'll measure oxygen production through photosynthesis, the rate of carbon dioxide removal, and biomass generation that could be processed into nutrients or biofertilizers. We'll also assess how efficiently the bioreactor performs under Martian gravity, radiation, and habitat conditions over an extended period. If successful, this experiment could reduce dependence on Earth resupply and become an important component of future self-sustaining Mars habitats. And now here are some of the instruments we're going to be using on the rovers themselves and back in our lab. Now I'm going to hand it over to Arya and Megan for engineering.
Okay, mission architecture. To maximize mission reliability, Alethea follows NASA's Mars architecture strategy by separating cargo and crew transportation. A heavy lift cargo vehicle delivers the surface infrastructure first, including the habitat, fission surface power system, ISRU plant, communications equipment, and scientific payloads. Before the crew departs Earth, these systems undergo autonomous commissioning where rovers verify that critical systems are fully operational. Only after successful verification is the crew launched aboard the Mars transfer vehicle. This phased architecture significantly reduces operational risk and ensures astronauts arrive at a fully functioning surface base. Mass breakdown. So the distribution, every kilogram sent to Mars is carefully planned because launch mass directly affects mission cost and feasibility. For Alethea, the total payload is approximately 30 metric tons, split between 17.5 tons and 12.5 tons. The cargo mass focuses on critical surface infrastructure, including the habitat, power systems, scientific equipment, and communications. The crew payload includes life support consumables, EVA equipment, medical supplies, and emergency systems. We've also allocated dedicated mass redundancy for spare parts and backup systems, increasing mission resilience and ensuring Alethea can continue operating even if critical components fail. Transportation systems. Precision entry, descent, and landing, EDL, enables safe delivery of crew and cargo to the designated exploration zone. NASA-inspired split launch architecture separates cargo and crew to improve mission reliability. Cargo lands first, autonomously deploying the habitat, fission surface power system, ISRU plant, and communications infrastructure. Surface systems undergo autonomous commissioning before the crew departs Earth. Crew launches aboard the Mars transfer vehicle, and the Mars 2020 Terrain Relative Navigation, TRN, enables precision EDL for accurate landing within the exploration zone. Power systems. Continuous electrical power is essential for sustained Mars operations. Our base is designed on NASA's Fission Surface Power Program, developed with the U.S. Department of Energy. This concept uses a compact 40 kilowatt nuclear fission reactor capable of providing continuous electrical power for at least 10 years. Unlike solar power alone, a fission reactor operates continuously through Martian nights and global dust storms, providing reliable baseload power for long-duration missions. To improve fault tolerance, Alethea also includes deployable solar arrays and lithium-ion batteries as a secondary and emergency power source. Communication systems. Alethea uses a hierarchical communications architecture based on NASA's Deep Space Optical Communications, a DSOC, technology. Instead of traditional radio waves, DSOC uses infrared lasers, allowing significantly higher data rates while using less power. A high-gain optical terminal on the habitat communicates with Mars relay orbiters, while a local wireless network connects rovers, drones, and environmental monitoring stations. Specific scientific data is then relayed back to Earth through NASA's Deep Space Network, providing a reliable, redundant communication system for both mission operations and scientific research. Surface systems. The surface infrastructure is designed as a modular, integrated system capable of supporting long-duration human exploration. At the center is a pressurized cabin which houses crew, laboratories, medical bay, and environmental control and life support, or ECLSS. Supporting infrastructure includes fission surface power unit, communication network, ISRU plant, water recycling system, and algae bioreactor. These interconnected systems provide redundancy and can be expanded for future missions. Surface vehicles and drones. Our Frontier Autonomous Science Rover is inspired by the European Space Agency's Rosalind Franklin rover and NASA's Perseverance mission. It is deployed before the crew arrives to conduct a terrain mapping, geological surveys, and environmental monitoring. Using a 2-meter rotary percussive drill, PanCam imaging system, Raman spectrometer, and ground-penetrating radar, it investigates subsurface materials that may preserve ancient biosignatures. The detachable Frontier drone performs aerial reconnaissance, producing high-resolution terrain maps, identifying hazards, safe routes for future extravehicular activities. Finally, the Sagan rover is our pressurized crew exploration vehicle that enables astronauts to travel safely across long distances while carrying other important scientific equipment. Redundancy. So, resiliency of Alethea is achieved through primary, backup, and emergency capabilities, and this image shows that for many different things.
So for our habitat structure, we decided to use an inflatable habitat with a layer of Martian regolith as our radiation protection. Our habitat includes individual inflatable modules, including life support systems, pressurized interiors, and airlocks. And compared to 3D printed habitats, inflatable habitats are a significantly lighter option, which allows for us to carry other materials within the weight limit. The inflatable habitat comes from Sierra Nevada prototypes, made from materials like Vectrin and Kevlar, which are flexible fabrics that can withstand cabin pressure. After the modules are inflated and set up, a rover will cover the habitat with 2 meters of Martian regolith, which will protect the habitat from radiation. Our habitat layout includes a central hub with 8 separate modules attached, as you can see in the layout drawn on the screen. For any type of space exploration, 2 types of suits are needed: an extravehicular activity suit, or EVA suit, for work outside the airlock, and an intravehicular activity suit, or IVA suit, for inside the cabins. We chose the Axiom Extravehicular Module Unit suit as our EVA suit because of its increased mobility and compatibility with all astronauts. It includes an easy slip-in process to wear the suit, and the EMU suit also includes a liquid cooling and ventilation garment, which Axiom partnered with luxury brand Prada to create. This EVA suit is currently under development to reach farther areas in space, making it the perfect option for our mission to Mars. For our astronauts' IVA suit, we decided to go with NASA's Orion Crew Survival System unit. Having already been worn by the astronauts in Artemis II's cruise mission, this suit proves to be a strong choice since it includes unique and compatible components that fit each unique astronaut. Like the Axiom suit, it includes a liquid cooling garment and a closed-loop system to provide crew members with oxygen and hydration. This suit is also the longest-lasting suit, being able to house astronauts for up to 6 days in a depressurized cabin. Together, we are confident that these suits will help astronauts explore and discover more on Mars. Our life support system includes MOXIE, or Mars Oxygen In Situ Resource Utilization Experiment, a water collection system in the ISS, and the Environmental Control and Life Support Systems, or the ECLSS, also used in the ISS. Our MOXIE system uses a method to produce oxygen from Martian air. This process produces oxygen by pulling thin air from the Martian atmosphere, compressing it, and pushing it through an electrolysis system, which produces oxygen and carbon monoxide as a waste product. Our water collection system utilizes a water recovery system that aims to recycle almost all water used. This process will be explained more detailedly in the next slide. Our water collection system utilizes ECLSS, which collects astronauts' breath, sweat, and urine. After being collected by a special air conditioner, the components are sent to a water processor assembly producing drinkable water. Another process our system will use to collect water is Oxyoplanum's clay materials with ISRU, or in situ resource utilization. This process includes drilling into the ground to acquire clay. The material is then sent to a pyrolysis oven where it's baked in high temperatures. Throughout this process, water vapor is captured and cooled, then it is passed through filtration and purification stages, producing water that can be used for drinking, hygiene, farming, and other needs. And now I'll pass it on to Abel and Neil for human operations.
All right, so crew selection. The crew selection process involves interviews, background checks, medication requirements, vitamin or health deficiencies, checks for response to different types of stimuli, and situational assessments. All crew members are required to have a master's degree or higher in a STEM field or have a medical doctorate. The final crew consists of 2 males, 2 females, 1 additional crew member assigned based on merit. The crew will be well versed in radiation environments and all types of possible mission problems, and all crew members will be cross-trained in combat medicine, engineering, cooking, rover operations, and first aid. All potential crew members will be tested on critical thinking, problem-solving, decision-making, communication, teamwork, and personality traits, as well as undergo multiple extensive psychological exams that assess their response to stress, isolation, and boredom, as well as their overall mindset. Next slide, please. Yeah, crew composition and roles. So, mission to Mars demands a highly functional, small, and efficient crew in which each individual possesses dual specialities. So, for our mission, we decided to compile a crew of 5 total members and have 2 of each role, 1 main and 1 backup, to ensure cross-functional redundancy. Here's why this specific 5-person crew was highly optimal for a Mars service mission. So, for our first crew member, we have the commander, who has a military background and is a systems engineer. A Mars mission involves high-stakes scenarios where a clear command structure and decisive leadership are crucial for the mission. And having a leader with a military background provides crisis management training. And paired as a systems engineer, this leader also understands how the habitat, rovers, suits, and life support systems function, allowing the entire team to troubleshoot better. Our second crew member is an analytical chemist and a psychologist. So as an analytical chemist, their primary role is to determine the exact composition, structure, and quantity of matter from the Martian regolith samples. And their secondary role as a psychologist is arguably the most important human factors role, as they check for any signs of depression, fatigue, or isolation-induced illness. Our third role is a trauma surgeon and a molecular biologist. If any injury occurs during surface EVA, a dedicated trauma surgeon is critical for standby to perform proper medical procedures. Paired with the skills of a molecular biologist, they would then conduct experiments to study the fundamental mechanisms of life at the cellular and genetic levels of the Martian regolith. Our fourth crew member is an astrobiologist and a habitat engineer. The primary goal of this mission is to find signs of past life, and the astrobiologist leads the search by investigating the origin, evolution, and distribution of life on Mars. By dual specializing as a habitat engineer, they ensure the structure's integrity is maintained. Our fifth and final crew member is a geobiologist and a physician. The job of the geobiologist would be to investigate the interactions between the planet's rocky crust, ancient water systems, and potential past life. As a physician, they serve as the primary medical officer during fieldwork capable of handling immediate physical trauma or environmental exposure out on the Martian surface. Soul schedule. To maximize efficiency, we'll have a 2-team rotation cycle where one team handles all major fieldwork for a day, while other team handles minor tasks around the base. Our first team is astronauts 4 and 5, and our second team is astronauts 1, 2, and 3.
Excuse me, you have about 1 minute left.
Oh. Okay, so yeah, this is the first part. Our second part is the work block. Next slide, please. Our third part is midday meal and sample handling. Our fourth part is exercise. Our fifth part is evening and wind down. And our sixth and final part is rest and recovery. So crew health and safety, it's from medical monitoring where the physician and trauma surgeon monitor biometric data twice during the day, once in the morning and once at night, and then they log all vitals back to Earth. The exercises to combat bone density loss. Every crew member has a mandatory 2-hour block of rigorous exercise using the T2 treadmill, the Advanced Resistive Exercise Device, otherwise known as the RED, and the cycle ergometer with vibration, isolation, and stabilization system, which is the SEVIS. For settling disputes, we have a framework that is designed to understand the problem, mitigate the tension, and maintain mission integrity. So we have mandatory cooling off periods where astronauts must step away from the situation for 30 minutes to regulate emotional response. Peer mediation, where a neutral third member will facilitate a meeting between crew members, and consensus. So a strict hierarchy is enforced if the dispute is already not settled by democratic consensus. The leader holds all tie-breaking authority, and yeah. Okay.
We must have frequent medical checkups to avoid emergencies. And since there's a 4 to 24 minute delay, the crew must act quickly and try to find like the nature of the emergency. They should also use emergency systems such as fire suppressions and etc. If an astronaut is injured, they must be isolated to prevent further injury while the trauma surgeon assesses them.
Okay, wrap it up as fast as possible, please.
The first human mission to Mars mission will be the most technologically demanding and most expensive, which is key to discovering new possibilities apart from our home planet. Thank you.
Thank you.
Thank you. Thank you.
Thank you, everyone. I hate rushing everybody, but we have like 18 teams to get through, so I appreciate you working so hard to get that done in time. So our next team is here. Go ahead and share your screen.
Okay. Can you hear me?
Yep.
All right. Okay, we're ready to start.
Okay, go right ahead.
Members of the Mars Society, respected organizers, and fellow competitors, good morning, good afternoon, and good evening, wherever you are in the world. My name is Sahil Modi, and I'm here today with Anshul Modi, and today we are proud to present Project Etheria, our proposed 18-month Mars surface mission to Arcadia Planitia. I want to begin with the core idea behind our mission. Etheria is not simply a mission to Mars. It is the first promise that a human base can become a living foothold, a scientific legacy, and the beginning of civilization beyond Earth. The name Etheria means celestial. For us, that represents more than going to space. It represents a mission designed to prove that humans can survive, operate, repair, grow food, extract resources, protect themselves, collect long-term data, and leave behind infrastructure that future crews can actually use. Project Etheria is built around one central question. Can Arcadia Planitia become a realistic foundation for future human settlement? To answer that, our mission connects science, engineering, and human operations. Scientifically, we study subsurface ice, radiation, dust, climate, biological stability, and Martian moons. From an engineering perspective, we design a reusable habitat, hybrid fission solar power, ice to life ISRU, rovers, drones, EVA systems, and radiation protection. From a human perspective, we plan crew selection, autonomy, emergency response, planetary protection, morale, nutrition, and health. Etheria is broad, but it's not random. Every system answers one of 3 settlement questions. Can we access resources? Can we protect the crew? And can future crews reuse what we leave behind? Next slide. Okay, why Arcadia Planitia? Project Etheria selects Arcadia Planitia because it gives us the strongest balance between water access, landing safety, terrain mobility, solar planning, and future expansion. It is also a major future SpaceX landing site. Our specific landing site is centered at approximately these following coordinates, and this location is in Mars's northern mid-latitudes, where orbital data suggests major near-surface water ice deposits. The most important number is the ice depth. Arcadia has water ice potentially accessible at around 30 to 60 centimeters below the surface.
That is mission changing because water isn't just not for drinking. It becomes hygiene water, greenhouse water, emergency storage, radiation shielding mass, and oxygen through electrolysis. The region also has an estimated 10,000 cubic kilometers of excess ice and a dielectric constant of about 3.15, supporting the idea that the buried material is relatively pure water ice. Arcadia is also safer than many dramatic science sites. Our selected region has less than 8 meters of relief, a regional slope under 10 degrees, and a rock hazard probability under 5%. That makes it more realistic for landing, construction, solar array placement, rover driving, and emergency return routes. We also compared Arcadia with the following other landing sites. So Jezero has a strong biosignature science, but more hazardous terrain. Geronimo's has thick ice, possibly up to 1 kilometer, but cliff and debris complicate mobility, and Valley Marinas has enormous science value, but relief up to 9.3 kilometers makes it unsafe for a first settlement readiness base. Well, Arcadia is not perfect, but local ice depth still needs confirmation, and dust can reduce solar performance. That is why Artheria includes 100 kilometers of robotic scouting, fission backup power, weather monitoring, and dust accretion research.
Core objectives and mission timeline. Project Etheria has 5 core objectives, each tied directly to long-term settlement. The first objective is settlement readiness. We evaluate Arcadia using terrain data, radiation maps, dust profiles, ice resource records, and EVA route validation. The second is Ice to Life ISRU. We extract subsurface ice, purify it, recycle it, and convert part of it into oxygen. Our water recovery target is 98% because every liter recovered reduces dependence on Earth. The third objective is long-term system degradation. Over 18 months, Etheria tracks how dust, cold, radiation, and low sunlight affect solar panels, filters, rover wheels, drone optics, EVA suit joints, airlock seals, greenhouse systems, and habitat protection. Solar array cleaning is triggered when output drops by 10 to 15%. The fourth objective is biological stability. Through greenhouse crop growth and our very own Vireo Bio program, our multi-generational fruit fly study. The fifth is leaving a tested foundation for future crews. Verified ice sites, water quality records, oxygen production data, crop data, rover and drone maps, shielding performance, repair logs, and emergency procedures. Ethereal also adds passive science through duration observation of Phobos and Deimos, using habitat-mounted, multispectral, and thermal cameras. This gives us Martian moon science without requiring extra risky EVAs. The timeline has 5 phases. Sols 1 to 45 are base activation. Sols 46 to 120 are baseline operations. Sols 121 to 260 are ice extraction, water purification, oxygen production, and crop trials. Sols 261 to 420 are full mission operations with extended EVAs, rover routes, drone surveys, armor inspection, and major science collection. And lastly, Sols 421 to 530 are final data collection, repairs, spare part organization, and site preparation for future crews. Next slide.
Crew operations, EVA safety, and autonomy. Project Etheria uses a 6-person cross-trained crew. Crew members are selected between the ages 25 and 35 using NASA/ESA style interviews and Etheria-specific testing for fitness, technical ability, communication, adaptability, and psychological resilience. The 6 roles are commander, systems engineer, medical officer, science specialist, ISRU engineer, and agricultural specialist. But every Marsonaut is cross-trained in EVA safety, first aid, and rover operation, as well as habitat procedures and emergency response. We also reserve 2 seats for women, while still selecting based on mission merit and crew compatibility. For EVA safety, planned EVAs are limited to 46 hours. Early walking EVAs stay within 1 to 2 kilometers of the base. No one goes outside alone. Each EVA requires at least 2 Marsonauts outside and 1 inside monitor. Before each EVA, the crew completes a 30 to 60-minute checklist covering suit pressure, oxygen, battery, tools, communication, weather, dust, and radiation. Every EVA keeps at least 30% oxygen and battery reserve. Abort triggers include low oxygen, low battery, low visibility, suit pressure warnings, and radiation alerts. This EVA system is supported by the ARC EVA suit, which includes exo assistance to reduce fatigue during tool use, sample handling, and repeated surface work. Etheria also pre-plans emergency modes for pressure leaks, fire, dust storms, rover breakdown, medical emergencies, water or oxygen failure, communication blackout, and quarantine. During power failure, the base can reduce to an 8 to 10 kilowatt survival load. Communication delay can range from about 3 to 22 minutes one way, so a theory uses local autonomy and a decision hierarchy. If safety, mission success, or morale is at risk, the commander leads, while the relevant specialist gives technical advice. Etheria also includes Aetherball, a crew-designed sport using 2 teams of 3, a foam ball, goal rings, and 3 5-minute rounds. It supports cardio, morale, teamwork, and stress relief.
Habitat architecture and life support. The center of Etheria is the Arcadia Shield habitat. The habitat uses a rigid structure called the Aegis core, made from aluminum-lithium alloy, giving optimal strength-to-weight ratio. This core contains life support, medical storage, communications, and mission control across 2 levels. Surrounding the core are 9 inflatable modules, each approximately 45 to 55 square meters. Together, the habitat provides about 500 square meters of total surface area and around 1,125 cubic meters of internal volume. This gives a 6-person crew space for sleeping, science, greenhouse operations, sanitation, exercise, medical response, storage, and emergency separation. The habitat is divided into clean, dirty, and emergency zone. That supports crew health and planetary protection because dusty EVA equipment and Mars samples should not contaminate sleeping areas, medical areas, or greenhouse systems. The most protected area is the Umbra radiation shelter, shielded using stored water, HDPE panels, and local regolith. The target is to reduce radiation exposure by up to 70%. For example, if an exposed surface sensor reads around 0.67 millisieverts per day, a shelter reading near 0.20 millisieverts per day would roughly show that 70% reduction in radiation. Radiation sensors inside the habitat, outside the base, along EVA routes, and on rovers create a local radiation map so future crews know where expansion is safest. Life support begins with 2,400 liters of Earth-supplied water in insulated tanks, but the mission targets 98% closed-loop water recovery, UV-led disinfection, and self-sealing EVA water bags. Sanitation waste is sealed, logged, and stored safely. The habitat is not just a shelter. It is a reusable base architecture that future crews can inherit, inspect, repair, and expand. Next slide.
Power grid and Ice to Life ISRU. Etheria uses a hybrid power system called the Arcadia Power Grid. We chose a hybrid system because solar power alone is too risky on Mars due to dust storms, low sunlight, and seasonal changes. The main source is a 40 kilowatt class fission surface power system using uranium-235. It is placed approximately 500 meters from the habitat and has an estimated mass of around 2,400 kilograms. Solar energy acts as the secondary source. Etheria uses 16 foldable solar panels producing about 19 to 24 kilowatts maximum output. They are tilted around 40 to 45 degrees to match the site's solar incidence angle and reduce dust accumulation. The solar system mass is approximately 850 kilograms. And battery banks provide emergency storage. They store about 250 to 300 kilowatt hours, enough to support about 20 to 30 hours of emergency operations, with an estimated mass of 900 kilograms. The most important engineering loop is Ice to Life ISRU. Robotic rovers first locate ice at depths between 0.3 and 2 meters. A sealed rotary percussive drill extracts ice regolith mixture, then sublimates the ice and pumps vapor upward. Purification also happens in layers. Physical filtration removes regolith particles. Vapor compression distillation separates salts and perchlorates, and biogalactic perchlorate removal targets around 90% efficiency. UV sterilization protects biological safety, then electrolysis splits water into oxygen and hydrogen. Etheria also includes a MOXIE-style carbon dioxide oxygen extractor as backup, targeting oxygen purity of around 98%. The total ISRU system mass is approximately 2,100 kilograms. If Etheria proves that Arcadia ice can be extracted, purified, recycled, and converted into oxygen, then future crews have a scalable path toward independence from Earth.
Greenhouse, food supply, and Vireo Bio. Etherea's greenhouse is a 50 to 55 square meter inflatable greenhouse divided into plant and vegetable growth, fungi and waste processing, grain and protein production, and water and nutrient control. The greenhouse uses more than 180 sensors to monitor water, atmosphere, humidity, temperature, root zone conditions, and nutrient balance. Mars agriculture cannot be guesswork. Every liter of water and every gram of nutrient has to be tracked. Etherea uses hydroponic racks and aeroponic towers instead of relying on Martian regolith. Martian regolith has 0% active organic matter, lacks natural fertility, and can contain perchlorates. Hydroponics can reduce water use by around 90%, and advanced aeroponics can reduce water use by up to 95% compared to soil-based farming. The crop plant includes PH04 peppers, potatoes, soybeans, leafy greens, and high chlorophyll crops. PH04 peppers are useful because they are self-pollinating and provide fresh flavor, vitamins, and morale support. The food supply is split carefully. 70% comes from earth-supplied packaged foods, including freeze-dried, dehydrated, vacuum-sealed, dry, and canned foods. 25% comes from greenhouse-grown fresh food. 5% comes from supplements such as vitamins, minerals, and spirulina backup. This means the crew does not depend on the greenhouse for survival calories. Instead, the greenhouse provides fresh nutrition, psychological support, and settlement readiness data. Etherea also includes our very own Vireo Bio program, which stands for Vitality, Inheritance, Reproduction, and Environmental Organism Biology. This program uses fruit flies in 6 sealed containers with up to 300 adults. Automated cameras track development, movement, reproduction, stress response, and radiation effects across generations. Fruit flies reproduce quickly, allowing multi-generational biology research without unethically experimenting on humans. This makes Vireo Bio one of Etherea's strongest biological science contributions. Next one.
Before I go on to this next slide, I just want to note that every concept figure is custom made. Okay, now Prospect and Argo rover systems. Etherea uses 2 major rover systems, Prospect and Argo. Prospect stands for Prospecting Rover for Observation, Subsurface Profiling, and Extraction Characterization Technology. It is an autonomous scout rover. Its job is to search for ice, map terrain, test regolith conditions, detect hazards, and validate routes before humans go there. Prospect uses rocker bogie suspension, an aluminum lithium frame, carbon fiber panels, MMRTG assisted power, and lithium sulfur batteries. It carries ground-penetrating radar, hydrogen sensors, near-infrared spectroscopy, and a PIXL-inspired X-ray fluorescence for perchlorate analysis. Its dimensions are approximately 2.2 meters long, 1.6 meters wide, and 1.4 meters tall. It performs 5 to 20 kilometer survey loops with multi-sol scouting that can extend up to 100 kilometers. Argo stands for Arcadia Roving Ground Operations Vehicle. It is a crew rover designed to carry 2 student Marsonauts along confirmed routes, and it is unpressurized. Argo uses an open-frame aluminum titanium structure, 4 sealed hub motors, metal mesh wheels, LiDAR, camera, and rover habitat communication. It has 90 to 120 kilowatt-hour battery pack. Argo supports up to 50 kilometers of confirmed routes. A typical 30-kilometer round trip at 8 kilometers per hour would take about 3.75 hours, fitting within EVA limits while still leaving oxygen and battery reserves. Argo's dimensions are approximately 4.5 meters long, 2.8 meters wide, and 2.2 meters tall, and the full rover system mass is about 2,100 kilograms. The safety logic is simple. Prospect goes first, and Argo follows only after routes are validated. This reduces crew risk and prevents unnecessary walking distance and makes EVAs more focused and efficient.
Falcon drones and dust degradation study. Etherea includes 4 aerial scouting drones called Falcon, which stands for Flight-Based Arcadia Local Cartography and Observation Network. Each Falcon drone is a compact UAV using electric vertical takeoff and landing, or eVTOL. Each drone has 6 rotors, allowing lift to be distributed across multiple rotors. This matters because Mars has a very thin atmosphere, so rotor area and efficiency are critical. Each drone has an estimated mass of about 10 to 12 kilograms, a folded size of about 1.2 meters by 0.8 meters by 0.6 meters, and a deployed rotor span of about 2.5 to 3 meters. During flight, Falcon uses around 2 to 3.5 kilowatts of power. A 20-minute flight is about 0.33 hours, so a 3 kilowatt flight uses roughly 1 kilowatt hour of energy used. To keep reserve power for landing, return, and emergency, each drone uses an estimated 1.2 to 1.5 kilowatt-hour battery pack. Falcon's safe scouting radius is about 2.5 to 3 kilometers. At an average speed of 20 to 25 kilometers per hour, a 20-minute flight could cover 6.6 to 8.3 kilometers of total flight path, but usable range is reduced because the drone must return safely. Falcon drones use LiDAR and cameras to create 3D maps before EVAs. They identify terrain hazards, dust conditions, navigation routes, and possible science targets. Etheria also uses a METI-type weather station inspired from the Perseverance rover to measure wind, temperature, visibility pressure, humidity, surface erosion, dust on solar rays, and atmospheric dust levels. This connects degradation data to real environmental conditions. Mars dust can reduce solar output, block filters, scratch optics, affect airlock seals, reduce rover traction, jam suit joints, and harm greenhouse systems. Etheria tracks degradation across the full 18 months. Solar cleaning is triggered at 10 to 15% output loss, and drone camera performance is monitored if image sharpness drops by around 30%. The goal is to leave future crews with a practical maintenance profile, how equipment fails, why it fails, and when repairs should happen. Next slide.
Mass budget and mission legacy. Etheria was designed to stay within the competition's 30,000 kilogram payload limit. Our total mission mass is 29,864 kilograms, leaving a remaining margin of 136 kilograms, or 0.5%. That means Etheria uses 99.5% of the allowed payload mass. The science total is 1,100 kilograms, including science instruments, radiation sensors, ice analysis tools, greenhouse research systems, VarioBio, Martian moon observation as well, and environmental monitoring. The engineering total is 22,792 kilograms. This is the largest category because survival depends on infrastructure and engineering systems. And lastly, the human operations total is 5,972 kilograms, which includes crew support, food, medical systems, exercise equipment, emergency supplies, hygiene, and operations. So Etheria also protects the scientific value of Mars through planetary protection, such as drills, sample tubes, gloves, tools, and containers are all sterilized, and clean and dirty habitat zones are separated, as well as rovers and drones scout sensitive areas before human access, as we mentioned. This prevents the mission from damaging the very environment it is trying to study. Project Etheria's legacy is not just that 6 Marsonauts survived for 18 months. The legacy is what they leave behind. Verified ice sites, oxygen production records, armor shielding data, crop data, VarioBio records, dust maintenance logs, etc. And to close, Robert Zurban wrote, Mars poses a critical test for the human race. How well we handle it will determine whether we remain a single planet constrained species or become spacefarers with the whole universe open before us. Project Etheria is our answer to that test. Thank you.
Thank you so much.
Thank you. That was perfect timing. And I believe we have about 5 minutes before the next presentation. Noah, you're here, correct? Noah C. Okay, is anybody else from your team here? Okay, so in 5 minutes, Noah, we'll start your presentation. So stand by, everyone. I'll pause the recording, take a stretch break, and we'll start in 5 minutes. Okay, we can see your screen. Go right ahead.
Yeah. So this is my Mars competition presentation. I made it all by myself. Didn't really have any teammates. But so I chose to land at the Perseverance rover landing site, the Jezero crater, because we already know the terrain partly because the Perseverance rover has been there, and because the Perseverance rover has a ground penetrating radar, we know that there's a lot of ice in the area. So water is not going to be as much of a problem. And if if the communication systems go down, then the Perseverance rover, it would be a long trip, and the Perseverance rover could act as a backup communication system. And then for crew housing, I chose to go with a prefabricated design. It can be expanded on, and they are pretty reliable for long-term housing. And they're fairly cheap in weight. For water, we chose the Jezero crater, so obviously there's a lot of ice. So we would bring drills, and we would go with the Moxie style electrolysis, which is initially taking water out of the soil from the ground and then putting it through a filter to make the water potable. For food, we will bring a little bit of prepackaged freeze-dried food, special occasions. But the main source will be insects and the algae spirulina, because insects reproduce extremely fast and they are a very good source of protein. But the crew needs to be trained on handling them because they can grow bacteria and then they will become not safe to eat. Oxygen so the primary will be closed loop air recycling, which saves 50% of air. And then there'll be Moxie, which is ISRU, sucking CO2 from the ground. Yeah, that's the air recycler. And then the rest will be the rock from Mars. And then there will be a little bit from Earth as well as backup. Energy, we're going to go with the hybrid system, which is a primary nuclear reactor with solar panels, because solar panels are not very sustainable on Mars. Because of all the dust storms and such, they can block the sun, meaning it's not very reliable. And then the nuclear reactor will be for those days that do not have dust storms. And then we'll go with the dual power source, one for life support and then one for everything else, lab equipment, and then like charging the rovers. The crew there will be the first one, the mission commander and the systems engineer. So he will be in charge of the mission, delegating tasks and such. The pilot will be piloting the ship, and the mechanical engineer, which is fixing things that break because it is inevitable, just like Thanos. Scientists, planetary scientists to study Mars, and then in agricultural entomology to handle the insects. And then there will be a medical officer and a communications specialist. So the communication specialist will be communicating with Earth, and then the medical officer is, as you can guess, will be handling medical emergencies. What the crew will be doing on Mars, they will be doing planetary meteorology, which is studying the atmosphere of Mars, paleontology, because the Jezero crater is very rich in water. There's a high chance that there was once microbiological, I don't know how to pronounce it, but there was once life on Mars, and the Jezero crater is a good place to study it, as well as studying weather. And then there will be human health research as well. So they will be studying the psychological, how the crew will handle Mars, being on Mars, isolated with only a couple other people. And we already know a little bit about the Jezero crater from the Perseverance rover. So we will be studying the Perseverance rover could not, making the place a very good solid place to land and grow upon. Traveling to Mars. The team will have one unpressurized rover, which is like the scouting, looking around, doing all the science and such. And then one pressurized rover for emergency, because like if the unpressurized rover gets lost a couple miles into Mars, like 2 miles into Mars, then it is unrealistic for the crew to have to walk back. But the pressurized rover will be sent out there to pick up the crew, and if they can, they will try to get back the unpressurized rover. And they will be, or the solar panel farm will also be used to power these rovers. There are a couple dangers that can happen on the trip, and on Mars. Dust blocks the solar panels for 6 weeks. The answer is that's why we have a hybrid system. The nuclear reactor can handle that. A crew member gets really injured, a medical officer will have to do their best, and they will most likely call Earth to get help. And then if the water extractor or the ESS fails, we don't have that, but it could have been something that we added. It was highly thought upon during making this. Someone will first have to find the problem, and then the mechanical engineer will have to fix it. And if they can't, then they will probably have to call her, or if we'll probably have to send down a new one, they will have to rely on their backup supply of water. The rover breaks down 80 kilometers away from base. That's why we have an emergency rover. The communication blacked out with Earth. The Perseverance rover is a way to do that, although one person would stay behind and try to get it back, maybe 2, 3 even. But yeah, the Perseverance rover could act as a backup. It is very far away, though, at this point. And then the crew has a mental health crisis. One, they have to ensure safety, like ensure that the rest of the crew is safe. They have to assess the situation, so they have to see what's wrong, see why the person is acting up, and then stabilize the person, and then contact Earth, and then remove from duty. So that person will not have any duties until he or she feels better. And they have to monitor him, and then he will recover eventually. And then the habitat pressure breach, bring duct tape. I listened to The Martian, and that's exactly what the guy did to fix his problem. I built this cool ship design, and then this is the only thing holding me back from setting mega mansions: the weight. I have an infinite budget with this project, but the weight is the only problem, and I calculated it. It will be 11,332 kilograms into space. That's all of the generators, that's the fuel, that's everything. Besides the ship. Why this mission matters. This is the perfect ending to my presentation. The reason why this mission stands out is because it's real, disciplined, and is engineered for the crew to be able to come back to Earth. I also drew up this mission patch as well. It's a cardinal because that's the team's name, and then that is the end of my presentation. Thank you, guys.
Thank you, Noah, for leading that expedition all on your own. It will be taken into account during the grading of the competition.
Thank you. I do not expect to win. I've seen other people's presentations, and they're awesome.
Well, that's much appreciated. Okay, so the next team doesn't start for several minutes and we want to stay on schedule. So we have 14 minutes before the next team is scheduled to start. So take a break, get a snack, and we'll be back in 14 minutes. Thank you, everyone.
Good morning, everyone. I'm Abhijay Prabhu. I'm from Team Sojourner, and today I'm presenting our mission architecture for our first crewed expedition to Mars, a mission built around one central question. Can Mars lava tubes serve as humanity's long-term shelter on the red planet? Sorry. Our mission sends a six-person crew to the surface of Mars for 547 days, or 1.5 years, within a strict 30-ton mass budget delivered across 2 launches. For our mission, we recognize that radiation exposure is the single most hazardous uh, driver behind our engineering decision. Our surface habitat is a temporary base, but the real long-term solution is underground in Martian lava tubes. To explore this, we land at the southeast base of Pavonis Mons, just 15 to 20 kilometers away from our primary target, a skylight. So our first phase can establish the habitat, and our second phase can begin lava tube reconnaissance without relocating the whole mission. Every decision in our engineering design traces back to just one number, radiation dose. NASA's research shows that conventional aluminum alloys or other metal alloys actually makes radiation exposure worse against galactic cosmic rays. Up to 63% worse, in fact, because they produce secondary particles faster than they can block the primary radiation. So our philosophy is simple. We want to minimize radiation exposure and maximize the use of Martian resources to preserve enough mass margin. Our landing site, for our landing site, we chose Pavonis Mons. And while some people might be asking why not choose another volcano like Mount Olympus or Arcia Mons because they have more skylights, we actually chose Pavonis because they have some of the best characterized skylights on Mars. High-rise imagery lets us plan with confidence and certainty, while Arcia skylights, while they are equally well mapped, they show signs of ongoing collapse, increasing the risk factor in our mission. For that reason, we chose Pavonis Mons to keep the crew safe during our mission. For our mission architecture and habitat, we use a two-launch approach. So first, the cargo and a robotic excavator called Rasor arrive 70 days before the crew, digging up enough regolith to shield our surface habitat before any crew sets foot on Mars. The habitat itself is two connected modules. One is a rigid core built from regolith and a radiation optimized composite. And the second module is an inflatable one, research and food production. Phase one involves setting up the habitat. So excavating the Martian regolith and building the habitat for the crew to arrive. Phase two is where the crew arrives and they start reconnaissance immediately. They are exploring skylights and nearby Mars terrain for signs of life and to record the geology of that area. For our life support systems, I'm going to go through water first because it is the most essential resource that we need. So for our water, we take 1.5 tons from Earth, and through the 547 days that we spend on Mars, water is recycled at 90% efficiency using the same systems that are on the ISS right now. And that cuts down a lot of what we need to bring from Earth. Our greenhouse, our InSight greenhouse, supplies about 10% of the crew's food using Martian regolith as a growing medium, and life support runs on a closed loop. The oxygen is generated from recycled water, and power comes from a 29 kilowatt solar array backed up by fuel cells and emergency radioisotope generators for dust storms. Our vehicle fleet includes RASOR for excavation, 2 utility rovers for daily operations, a pressurized rover for long expeditions, a dedicated scout rover to the secondary cave site, and a small drone that maps the lava before any human even enters it. All told, we're using about 28,000 of our 30-ton budget, leaving just enough margin for any other weight that we might need to carry. So our first experiment focuses on one of the biggest challenges today on Mars. Unlike Earth, Mars doesn't have a thick atmosphere or global magnetic field, so the surface is constantly exposed to radiation for space. Over billions of years, this radiation gradually damages and destroys organic molecules that could provide evidence of ancient life. Our goal is to determine whether going deeper underground naturally protects those molecules. We want to identify the minimum depth where radiation becomes low enough, biosignatures from life are much more likely to survive. If we can correctly identify that depth, future missions will know exactly where they should look for biosignatures instead of exploring randomly without any focused effort. And this is how we plan to do that. Our second experiment begins by setting up several sampling stations throughout the lava tubes. These stations start at the skylight entrance and continue every 20 to 50 meters until we reach the deepest safe location. At each station, we first record the surrounding environment, including radiation, temperature, and humidity. Back inside the habitat, these samples are analyzed using instruments such as Raman spectroscopy, GCMS, and X-ray diffraction. By comparing the chemistry and mineralogy of samples collected at different depths, we can determine where radiation damage begins to decrease and where organic molecules are preserved more effectively. Our next experiment sorry, our next experiment runs for the entire mission because habitability isn't really something we can measure in a single day. An environment like an underground skylight might look suitable 1 week, but experience a large change later on. And to understand whether these skylights and lava tubes can actually support life or microbial life, we need to know how stable they remain over time. So this experiment focuses on long-term monitoring. Instead of asking whether a lava tube is habitable today, we're asking whether it stays habitable over months or even years. Stable temperatures, low radiation, and the possible presence of water are all important factors that could make these environments suitable for life. So early in the mission, the crew installs permanent monitoring stations throughout the lava tubes, and these stations continuously record temperature, humidity, radiation, pressure, gas composition, and water activity without requiring astronauts to be present all the time. Every month or two, the crew returns to each station to download the data, check the equipment, and collect additional geological samples. At the end of the mission, we compare all of the measurements to see whether the underground environment remained stable or changed over time. And this is our third experiment. So most life detection systems today search for molecules that are common in life on Earth, such as DNA, proteins, or amino acids. The problem with that is if life on Mars formed differently than on Earth, it might not contain any of those molecules. Instead of assuming that Martian life looks like Earth life, the experiment searches for broader signs of biology. We focus on chemical complexity, repeating molecular patterns, and any chemical organization that could suggest biological activity, even if the chemistry is completely different from anything that we currently know. Every sample collected during the mission is examined using several different instruments. Rather than searching for one specific molecules, the instruments look for patterns that are difficult to explain through normal geology alone. An AI would then compare all of the chemical data together to identify unusual combinations that deserve further investigation. If a sample is flagged as interesting or unknown, it is tested again through different instruments before any conclusions are made. And this brings us to one of our last experiments. So finding an unusual molecule on Mars doesn't automatically mean that we found life. Many geological processes can actually produce chemicals that look biological. Because of that, scientists never rely on a single piece of evidence. This experiment focuses on determining what makes a biosignature scientifically reliable. Instead of asking whether we found life, we're asking how much evidence is needed before a biological explanation becomes the most likely one. Whenever a potential biosignature is identified, it isn't accepted immediately. The sample is analyzed several times using different instruments and compared with its surrounding geology and environmental conditions. If multiple independent observations all point towards the same conclusion, our confidence in that biosignature increases. By the end of the mission, the crew will combine all of these results into a biosignature confidence framework. This framework could help future missions decide whether a potential discovery is strong enough to justify further exploration or even a sample return to Earth. Although these are presented as four separate experiments, everything what I've shown you is actually designed to work together. The first experiment tells us where biosignatures are more likely to be preserved. The second determines whether the underground environment remains stable enough over time for biosignatures to survive. The third develops methods for recognizing life that might not resemble what we know as life on Earth. And finally, the fourth combines all of the evidence into a framework for determining whether a biosignature is truly biological. Together, these investigations aim to answer one of the mission's central questions. Do Martian lava tubes preserve reliable evidence of ancient habitability? And should they become the focus of future exploration? Our six-person crew here is built for redundancy. A commander, a pilot, a flight surgeon, an instrument engineer, astrobiologist, and systems engineer are all present, but every one of them is also cross-trained so that they are available to step into any other role in the case of an emergency or anywhere where they're needed. Their days are structured around research and fieldwork with flexible scheduling and protected personal time each day.
You have 1 minute to finish up.
Okay. So for health and well-being, essentially, we're just scheduling regular psychological check-ins and community time every day to make sure that astronauts' mental health is stable and not disrupted. And that was it for human factors. And I just wanted to conclude with saying that every part of this mission, the engineering, the science side, and the human factors, is really built around one idea to establish a safe, well-sheeted surface base first, and then use it as a base to answer a platform to answer our real question, whether Martian lava tubes can become the shielded, stable homes that make permanent human presence on Mars possible. Thank you for your attention.
Thank you so much. Great presentation. And I made a mistake on the schedule, everyone, by 5 minutes. So are the Red Pioneers here? Anyone from the Red Pioneers? M. Tierney, A. Smith, K. Herrera at Goodwin Magnet System. Please let me know. Okay, if anyone from Red Pioneers is here, let me know. Okay, we will wait for the next time. Is anyone from Orion here? Also Goodwin Magnet System.
I'm here. It's Amethyst from Team Orion.
Okay, we will start at 2:30 Eastern.
Got it.
Okay, so we will start in 24 minutes, everyone. I will pause the recording and we will start again at 2:30 Eastern.
I'm going to start to call my team right now.
Okay.
All right. Good afternoon, Mars Society. We are Team Orion from Rivertech at Gowan University. So we wanted to point out before we start just like presenting everything, instead of a PDF, we did send you a Google Sites with all the information, and we also added a document version. So if you want to see the document version, it will be on the website. But now we're gonna start presenting now. So our teammates are Antonella, Aiden, Grant, Tiago, and Melissa. So, and Amethyst, that's me. Hold on, give me a second. My computer is not working for some reason. So what we were trying to do is get at least 3 teammates onto here, so each of us can do one of the 3 main slides. But because Melissa can't come on here, I will do her slide. That's fine with me. So welcome to Team Orion. You're basically in our universe now, so welcome. I haven't seen this thing in 2 days because internet and the thunderstorm that happened a few days ago. So I haven't seen anything. So I'm going to be struggling. So that's a warning. So Orion is constellations in the sky. Orion means hope and strength to us. These past weeks we've been doing research and working on it every day when we had the chance. Sometimes we made mistakes, but that's okay. We are going to start with some notes that we had for our spaceship designs from our lovely team member Antonella. You probably might not be able to see a few, but that's what they look like. Now we're gonna head to the science part of all this. So basically, so we were trying to imagine if we were in Mars, what would we actually kind of do? So we're just So we're gonna take this 1.5 years to research different things on Mars. Like, is the water gonna be /ice gonna be safe enough? Are we gonna be able to plant things? Is that gonna be possible? This has also been sent to you, Nicole, so you can look at it. So you can look at this as well. So yeah, that's the science part. The habitability part, I think, is the next one. Sorry, my internet's a little slow. So habitability, we had some ideas from the way an RV works when you like press a button and it kind of spreads out. The Transformers movie and an idea that Mr. Harbinuk, a River Tech teacher from our school, that has given us an idea. We had an idea to start making our spaceship full of like a bunch of stuff into our environment that we will live in, and then when we need to start traveling, we can start pressing a few buttons and it will turn into traveling mode and can travel on the planet as well. So we have that over there too. And then the science part, which my teammate either Aiden or Melissa is supposed to do, but I don't think they're in here today. I think it's, oh yeah, okay, it's on here. So our plan was to have our rocket turn to different vehicles. I think we already got that down, but we were supposed to have different vehicles turn to like different vehicles, kind of like how like one of those like vehicle toys that you see that can turn to like different other things. That's also what we got inspired by, and that's how we got it. That's where we got our inspiration. Let me see if I can find a way to get out of here. Hold on, wait, that's why it exists. And calm down, chillax. Wait, what the hell happened? Heck. Okay. Sorry, I'm struggling here. Give me a second. What is going on? I'm trying to figure out how to get on here. My bad. Hold on. Found it. Nope, still wrong thing. Found it. Can you load, please? Do you want to load?
If your internet is lagging, it might help to turn off your camera.
Oh yeah, sorry. Hold on.
No problem. I'm just trying to help.
Sorry, we're spending all morning doing the final touches. We were stress eating in the process, so there's a lot of stuff going. I'm gonna have Antonella go over this. So Antonella, are you still in the Zoom meeting?
Yeah.
I'm gonna stop sharing. Can you screen share, please?
Yeah, the presentation, right?
Can you go over the website with people since you were in charge of the website?
Okay.
All right, thank you so much. I'm going to stop sharing. And I will turn off my, and then I'll turn off my microphone and Antonella can go ahead. If this thing can load. As my screen pitch white.
Antonella, if you're speaking, we cannot hear you.
I think she's trying to figure out how to screen share real quick. Just give us a second.
We could see the screen. We just
Oh,
couldn't.
okay.
hear anything.
Oh, she just sent me a text real quick. She says when I share, I can't talk. So let me figure this out because my screen's pitch white for some reason. Very sorry. I might have to leave and come.
Okay, just know the next team is here and we will start them at their scheduled time. Thank you everyone for your patience while we wait for the team.
All right,
to-
I'm back. Let me just figure this out real quick. The only computer in my house had to be in the room with the least amount of internet. Great. Just give me a second. Also, warning: I wasn't in charge of the website. I was mostly in charge of the Google document that we were working on as well with 2 other teammates. So I have no idea what's on this thing. So I come to update to see how people are doing sometimes, but to be completely honest, I don't really know what's on here. So please. There might be stuttering amethyst madness that some people say when I present things. So please be patient with me.
It's okay.
All right. Let me. What just happened? I'm so frustrated. It's almost, we have 10 minutes left. Are you freaking kidding me? Okay, it's okay. Calm down. I know this. You're fine. You're fine. Okay. Oh, there we go. Figured it out. Let's go. All right. You guys see it now?
It's coming.
All right. So this was our website. This picture has been found by, I'm pretty sure, Melissa. I don't know if it's Melissa or Antonella. They were both in charge of this. So you guys can choose which tab you get to start in. I'm gonna let you guys choose because I don't know where to start.
Let's start with science.
Okay. If I can get there. There we go. If this thing can hurry up. There we go. So we were also gonna there's some typos in this. We were gonna test the oxygen or something. I don't know. I think Melissa just put that there. I don't know. We were also studying if the ice is able to be being melted down and to drink safely, because some people have said that there are also chemicals in that ice, and we want to make sure that's true or not. So, is there a subpage? Oh, there is a subpage. Okay, there's a subpage, I guess. Oh, they actually had a good idea on that stuff. Water. What do they put down here? All right. Why ice matters. One of the robot's first jobs is to search for underground ice, and water is one of the most important resources for the Mars mission. It can be used for drinking, growing plants, producing oxygen, and making rocket fuel. After finding a safe location with ice, the robots begin to prepare the areas for future habitats. I actually recognize these notes. I'm pretty sure these notes are from Melissa. I think so. This full page. Robots mission before astronauts travel to Mars. An autonomous robot is sent ahead. Its mission is to explore the area, find underground ice, and I think we already went over this on the top. And I think, yeah, it says the exact same thing over here. So I think that's it for science. Wait, no. The subpage has a subpage. Okay. Ice. Did you put anything under here? So we were working on it, but the thunderstorm that happened this weekend was getting us unable to work on this, so some of it might be unfinished. So this just explains everything in the last one. Okay. Let's go to engineering, I guess. All right. So like I said in the Canva slideshow that I did, there's some more notes by Antonella right there. So we had the idea from Mr. Harbonock, a River Tech teacher who is teaching us science. The Transformers movie, in a way, an RV works. We can try to make different parts of the
If you're there, Amethyst, we lost your sound. Well, I hope we get that team back, at least someone from that team. While we wait, we will stand by for the next team that will start in 7 minutes.
Okay, can you see the presentation?
Yes.
Perfect. Well, to start, we are Cutis Mission. We are from Costa Rica, and we are a group of 6 persons. And today, we are going to present our proposal for the mission of Mars. Start with the science part.
Well, today in our presentation, we are going to present our objective, our landing site, and the 3 parts of science, engineering, and human operations. We will start with this objective, which is to examine the geological, atmospheric, and chemical characteristic of Mars, including the factors responsible for the disappearance of liquid water, the composition and accessibility of natural resources, and the scientific and technological approaches for the sustainable use, with the purpose of assessing the planet's habitability and its sustainability for the future human exploration and colonization efforts. Then we have the science part. Well, we first want to talk about the glaciers, and to start, we have some facts that were measured in the landing area, which are that we have confirmation by the chart radar, which gives us a dielectric permittivity of around 3.1, which tells us that the ice around the area is almost 100% pure ice. It is not 100%, but it's very close. Also, the thickness in this area is very great because it has between 50 meters and 1 kilometer, depending on the area. Also, they form during periods of high margin obliquity, and the layer of dust on top protects them from sublimation. So why talk about glaciers? Well, we have to understand that glaciers are very important, not for just this mission, but also for the missions here on Earth. The paleontology, the geological analysts here on Earth analyze a lot of the glaciers in the Antarctic area because they have bubbles inside each layer, and these bubbles have a lot of information that were formed in the atmosphere. So by analyzing each layer of the glacier, of this ice, we can get a lot of information about the periods, different time periods that these glaciers were formed. Also, in the base of the glacier where the ice meets the rock, this zone it has not been contaminated with radiation, which is essential for a deep analysis in the ice and in the water to get to know better the situation around earlier period times. Then we have the Erebus Montes. They are really important because they have the Noachian rocks. These Noachian rocks are very old, around 3,700 million years ago. They formed, and they formed when Mars still had liquid water, and they contain phyllosilicates. These are minerals that are essential because they only form when the minerals were in contact with water. So by analyzing these rocks, we can get a lot of information to contrast with the previous information we got from the glaciers. Then why we chose the landing site in Albamons? Well, we chose this landing site because it has a lot of ice confirmed by the SWIM project, which is an essential project that happened a lot ago. This SWIM project gave a score above 0.5%, and this score is really great because it indicates a lot of presence of subsuperficial ice. Also, it has intact lava tubes, which are essential for all to our base. Less than 50% were collapsed, and also they are very wide. And the last
essential part for the landing site is that it has a lot of geological diversity. This geologic diversity is essential for us to analyze the different contexts in the area to have a very good analysis to the water and ice.
Okay, so we are going for the conditions for the past life. First of all, for open months to have super life, well, we saw that we need three conditions: liquid water, an energy source, and available nutrients. Phyllosilicates detected in the area revealed that a landscape by water, and some show signs of forming under high temperatures, fitting a volcanically driven hydrothermal system. Okay, we search for biosignatures using three lines of evidence. First of all, we have morphological, the microtextures in minerals resembling microbial structures. Then we have chemical curiosity, already detected the largest organic molecules ever found on Mars, proving organics can survive billions of years of radiation. And isotopic carbon and sulfur fractionation patterns that differ from purely chemical process. Okay, today Mars' surface is cold, irradiated, and dry, hostile to life. That's why the surface matters. Where the ice meets with the bedrock, the conditions are far more stable, giving any past biological material, which is the best chance of the survival for us. Okay, the landing site selection comes down to basically the water. We follow NASA's SWIM project, which combines orbital data to locate accessible surface ice, some radar soundings, then confirm how pure is the ice, letting us distinguish rock, sand, and ice with confidence. The atmosphere itself is a resource. MOXIE already proved oxygen can be extracted from Martian CO2, succeeding 16 times on Mars. On the ground, volcanic regolith can be 3D printed into shielding, and nearby lava tube take protection further, cutting radiation exposure up to 82% compared to the surface. Okay, our instruments mirror proven technology. First of all, we have crescent type imaging maps minerals from a distance. Then we have shadow type radar, which distinguishes rock, sand, and ice underground. And last but not least, we have Sherlock type spectroscopy, which flags organic biosignatures without disturbing the sample. Okay, our sample strategy has three steps. First, we prioritize clay-rich sediment, the kind that revealed over 20 organic molecules elsewhere on Mars. Second, we analyze it with a laser spectrometer, gas chromatograph, and mass spectrometer. And third, we preserve the untouched samples in sealed containers for a possible return to the Earth. And all of those leads comes to these conclusions. Our data help assess long-term availability. MOXIE shows that astronauts could live off Mars on resources. Lava tubes offers the best natural radiation protection, and the future settlements should prioritize the same criteria that we used here, like the lava tube access and the ice purity and geological diversity. Well, we are going to the engineering part with my partner, Johan.
Well, we know that the engineering part is one of the strongest parts in this mission. But to continue, before building the habitat, our mission starts with the Bridgehead Exploration System, an autonomous robotic platform that prepares the landing site and reduces mission risks. First, it scans the area using ground penetration radar, LIDAR, cameras, and thermal sensors to create 3D maps, detect underground ice, and identify the safest construction site. Next, a robotic drill analyzes the soil, while an Ingenuity-inspired drone explores nearby lava tubes to verify that they are safe for the habitat. You can think of the bridgehead as the excavator at the beginning of a construction project. Before building starts, it studies the terrain and makes sure everything is ready for the crew. Once the site is approved, we begin deploy the habitat. First, all critical systems are checked, and the nuclear reactor is activated to provide continuous power. Autonomous robots then prepare the lava tube by clearing debris, leveling the ground, and installing power and communication lines. Our habitat is a 5-level vertical structure for 6 astronauts. It includes laboratories, crew quarters, life support systems, and control center. 2 additional modules provide storage and a gym, while a separate hypodronic greenhouse produces fresh vegetables and support oxygen generation. The lava tube is our main radiation shield, while weather tanks and Martin regolith provide extra protections. All systems, power, water extraction, oxygen production, and food cultivation work together to create a reliable and self-sustaining base. To explore the surrounding region, we use a pressurized rover based on NASA, a small pressurized rover concept. It carries 4 astronauts for mission of up to 2 weeks and also works as a mobile laboratory, equipped with GPR, LiDAR, cameras, thermal sensors, Raman, and LIPS spectrometers. It can detect underground ice, analyze rocks, and explore the new lava tubes. Autonomous cargo rovers transport equipment and scientific samples, reducing astronaut workload and improving mission efficiency. Astronauts perform every EVA wearing advanced spacesuits that work like a small personal spacecraft. The suits provide oxygen, remove carbon dioxide, regulate temperature, and protect against dust and extreme temperatures. Biomedical sensors continuously monitor the astronaut's condition, while radiation exposure is controlled through careful mission planning and time limits. Finally, our entire engineering design stays below the 3 tons competition limit. The habitat is the largest component at 8.5 tons, followed by the mobility system, life support system, and the nuclear power system. Scientific equipment, consumables, and dedicated safety merging complete the payload. Our total estimated mass is 27.5 metric tons, leaving 2.5 tons of available margin. This demonstrates that our design is not only technically feasible, but also realistic for a future human mission to Mars. And to continue with engineering, we have the oxygen production.
Okay, so in this part of the presentation, I will explain how our Mars base produces oxygen, generates electricity, and protects the astronauts. These systems are important because the crew will live on Mars for a long time without regular help from Earth. First, let's talk about oxygen production. Our base get oxygen for 2 sources, electrolysis and plants in the greenhouse. Electrolysis use electricity to split water into hydrogen and oxygen. The oxygen is stored and sent through the habitat so the astronauts always have air to breathe. The water comes from ice below the Martian surface, and the electricity comes from our nuclear reactor. Now, let's talk about energy. Okay, so our main power source is a small nuclear reactor because it provides electricity all the time and even during long nights and dust storms. All the important systems such as life support, water recycling, lighting, and communication depend on this energy. We also have backup generations that keep the essential systems running if the reactor stops working. Another challenge in Mars is those storms. To stay safe, you we our habitat is built inside a lava tube. The rock protects the astronauts from dust and creates a safer environment. Air filters and sealer systems also stop dust from entering the habitat. And finally, we must protect the crew from radiation. The lava tube blocks much of the harmful radiation. We also use a 50 centimeters layer of water around the living areas and add Martian soil around the entrances from extra protection. In conclusion, our Mars base use oxygen production, reliable nuclear power, backup energy systems, and a strong protection against dust and radiation. Together, these systems make the base safer for long time missions of Mars. Let's continue with human operations.
Okay, now we will continue with human operations section. We explain how the crew is organized, how daily operations are managed, and how astronauts are protected during the surface activities. First, our mission uses a 6-astronaut crew. This number allows to cover the main scientific, medical, engineer, and operational needs of the mission. We are increasing the demand of habitat space, food, water, and life support system too much. The crew include a commander, a pilot, a physician, a geologist, a geologist, an astrobiologist, a mechanical engineer, and a system information engineer. Each astronaut has a primary role, but they are also cross-training in secondary responsibilities, so the mission can continue safely if someone is unavailable or if an emergency occurs. For selection and training, the crew is chosen not only for technical expertise, but also in teamwork, emotional control, and compatibility. Since this is an isolated 18-month Mars surface mission, astronauts would be able to work under pressure, solve conflicts, and make autonomous decisions where real-time support from Earth is not possible. Moving to daily operation, the mission is organized around safety and continuity. Each show begins with health checks and system reviews, including habitat pressure, oxygen production, water recycling, power, and communication. The crew then divides tasks between science work, maintenance, instrument monitoring, road preparation, exercise, and rest. Server access is not controlled through a protected habitat at the zone, where the crew checks tools, readiness, EVA equipment, and emergency supplies before going outside. Personal rovers also support exploration by reducing continuous EVA exposure and allowing the crew to reach more distant scientific targets. And finally, the EVA system protects the astronaut during the surface exploration. This will support sampling, instrument and deployment, rotor operation and maintenance. It deploys oxygen, carbon dioxide removal, thermal control, communications, and biomedical monitoring. It also reduces fatigue through mobility, visibility, and ergonomic design for safety and reliability. Evaluation limits reduce radiation and environment exposure, and the suites are inspected before and after each EVA. Those controls, spare parts, and preventive maintenance help keep EVA operations reliable through the mission. Now, my teammate will continue with the next part of the mission.
Now, focusing more in structure and medical topics, housing a 6-person crew inside a lava tube for 18 months solves the radiation and thermal problem, but creates new human factor challenges. Each crew member needs a minimum of 28 to 29 cubic meters of habitable volume, with rest and hygiene areas physically separated from exercise, waste, and maintenance zones to avoid friction. With zero natural daylight for the full mission, the dynamic lighting becomes the crew's only substitute for a circadian cycle. Blue enriched light during work hours and blue depleted before sleep. Medically, there is no evacuation and no real-time telemedicine. Every event is handled on board. That's why exercise is treatment, not optional. 2.5 hours daily of resistance and cardio training, since without it, muscle mass can drop up to 30%. Feeding 6 people for 18 months requires between 3,300 and 5,900 kilograms of food. Next. Now, behaviorally, this is one of the highest risk missions modeled. Isolation plus a communication delay of up to 44 minutes each way removes real-time psychological support. As Earth shrinks to a point of light, crews report anxiety and depression, the Earth out of view phenomenon. And the Martian soul at 24 hours, 39 minutes conflicts with the human biological clock. The response: rotating leadership and staged conflict resolution, peer-to-peer, then meditator, then full crew. Conflict here isn't failure, it's expected and managed. Next. So this was our mission, Acutis mission. I hope you all like it. Thank you for your attention.
Thank you so very much. Wonderful presentation. Just finished in perfect time. And is our next Noah D and Jacob D. Are you guys here?
Yeah.
Okay.
Yeah.
We will start in 5 minutes just so we can keep time. All right. See you guys in 5.
Okay. So good afternoon. My name is Noah, and our team name is Olympus Mission. Today, we're laying out the blueprint for human survival on Mars. So I will be walking through the core landing and habitat and communication setups. Okay. So landing site. Our targeted landing site is the Tharsis Volcanic Province. We picked this spot because it's flat enough and for a safe automated touchdown. But more importantly, it puts us right next to the subterranean lava tubes, which provide natural shelter and from cosmic radiation and extreme cold. The Tharsis province gives us the perfect mix of landing and safety and natural geological armor. So, Jacob, I think you're next.
Deployment. Built from an internal structure, the inflatable membrane is deployed autonomously on the surface. The technology's heritage directly utilizes spaceflight heritage proven by the Big Blow Expandable Activity Module on the ISS. Habitat yields total mass. The habitat yields a total mass of 1,412 kilograms, providing a comfortable living/working volume of 565 cubic feet, with reliable built-in protection against solar radiation. NASA demonstration. Expandable habitats radically optimize space missions by solving strict rocket weight and volume constraints. Adaptive membrane design. Membrane engineered with integrated Kevlar and Mylar lasers establishes immediate internal volume and airtight seal. We will also bring 3D printing robots to Mars to 3D print a layer of regolith around our inflatable habitats to protect them from radiation. And we can also use the habitats to print new habitats. The 3D robot to print new habitats. We will also send a small satellite to Mars to establish communications with Earth, but due to the distance between Mars and Earth, there will be a delay in communications. Protection. To protect the crew from harmful radiation, we will land the hab inside of a lava tube so that it will be covered in a layer of regolith to stop the radiation. Also, the lack of gravity can cause muscle weakness. To fix this, we will pressurize the habitats to prevent this. But on the way to Mars and on the way back, they will need to exercise a lot to prevent harmful side effects of low gravity. We will also have a security system in the habitat to make sure the pressure and oxygen levels are safe.
For now, even if everything goes perfectly with the engineering and the astronauts are perfectly trained physically, the mission could still fail due to the human factor of isolation, being far from home. Living in a confined, high-stress environment, it could lead to depression and behavioral changes. The way the architecture mediates its connection to the external environment is deeply important, not only for physical safety, but also for the crew's psychological connection to the Martian landscape. While some designs utilize more functional dome-shaped organizations that separate operations into distinct pods, these multi-pod structures are highly efficient in terms of applicability because you can build more of them and connect them easily. However, a crew's mental health can deteriorate rapidly in these types of rapid arrangements because they are highly monotonous. Astronauts end up looking at the same spaces at the same walls from every angle, with very physical separation between functions. By understanding this spatial relationship, our design rejects repeated pods and stable organizations that build over floors. While humans have developed a level of rationality before we act. Consequently, our reactions, spatial needs, and behavior remain heavily influenced by survival instincts. The vertical layout is more suitable for long-duration missions in challenging technical environments. Our does so through circular strategies. For example, to reach the laboratory, one has to pass by the kitchen and recreational areas. These transition moments help to naturally encourage social interactions, rather than a static, completely open space. Any mission to Mars needs a source of power, whether it be a rover or a lander, that needs this electricity to meet their ideal task or manned missions where this power actually keeps the astronauts alive by giving them oxygen to breathe and water to drink. So, what source of power we will use? Basically, solar and nuclear energy. These two are the sources that we will use. Let's start off with solar energy. The benefit of solar panels is that they are relatively easy to maintain and put up. Some of only maintenance that will be needed is maybe rewiring or cleaning of the panels after a dust. We have very thin sheet solar panels that we can create now that are very light, that just like a thin sheet of plastic. But the solar energy of Mars is a bit thick. Mars solar irradiance is about half about the Earth. Using sun tracking solar panels can increase solar energy production by 30 to 14%. Now, let's talk about nuclear energy. That we already is very powerful. This means that it doesn't take up a lot of space and it always functions, whether it be day or night or during a dust storm. One of the main downsides to nuclear energy is the maintenance. Astronauts will have to understand the ins and outs of the entire reactor and how to fix it. Anything went wrong and if a colony has dependence on one or two nuclear reactors and one of them has to fail, that will be catastrophic to the colony. However, NASA is trying to fix the maintenance problem. They're working on a project called Kilo Power, which is making small nuclear reactors that create anything from 1 to 10 kilowatts of power that can be used to send to Mars. Nickel. This mission needs a way to travel Mars. That's why we are using a new type of rover for astronauts. This vehicle is huge step forward because it has humanity to ride in this space. It to run on regenerative fuel cells that produces electricity from sunlight and water. The same regenerative fuel cells could also be used to supply electricity in areas such as refugee camps.
Your sound is very, very low. You need to fix your microphone or something.
And disaster strike place. Once board and pressurized, the astronauts are expected to be able to survive inside, even without spacesuit. The aim also is for two astronauts to be able to board and live in the rover for about 30 days, while they explore the surface of Mars. Once the astronauts establish their base and they base in the lava tubes, the mission to scan the lava tubes initiates to find protections against radiation, meteorites, and the cold weather. Also researching for ice resources and potential signs of microbial life. For this, we will propose to use the Boston Dynamics robots and the Dual Axle rover. These robots are designed to explore areas that will be inaccessible, such as prairies and lava tubes. These robots will help integrate TLS and MM sensors. The TLS is a high accuracy LiDAR strategy interval to capture and limiter accuracy. 360-degree points close of surrounding rock, and the MM allows researching to generate 3D points clouds while walking continuously through the cave. While the robot collects the data, it will process using a specialized software to create an exact digital twin. Also, the robots will carry a rotary percussion drill that will have the same principles and idea of its predecessor, the Curiosity robot. The robots will create a small payload below using percussion and monitoring resistance to catch the rock harness before committing to a full hole. The drill beats both spins and hammers simultaneously to pulverize Martian rocks. It bores to maximum depth of to 6.4 centimeters. The pulverizing action turns the rock into a fine powder, which travels up a system of clouds around the drill bit. The drill mechanism then shifts and gathers this dust. Later on, the astronauts will have the samples and use the same in the laboratories to find if there is life or the components of the lava tubes.
Okay, so to look at how space radiation and low gravity affects life, we're running a embryology experiment. We're using synthetic silicon egg, chicken egg cell, designed by Colossal Bioscience. The membrane lets oxygen pass through while keeping the moisture trapped. So by shipping lightweight, fertile eggs instead of adult chickens, we save cargo mass and eliminate heavy food requirements during the transit. So regolith is contaminated with toxic perchlorates, which are harmful to humans and plants. So to fix this, we put some raw regolith into big climate-controlled vents. Then we use a special NASA engineered bacteria called Bacillus subtilis, and the bacteria basically eats the toxins and breaks them down. And essentially all that's left is table salt. And it also creates some extra oxygen. So for food and water, we'll be using the greenhouses, and we're going to bring our main source of food is going to be food grown in the greenhouse, but there'll also be some rations just in case that goes wrong, and also for time in transit. So for food production, we are deploying automated vertical greenhouses by building a safe farming soil with a regolith. We essentially just use aeroponics, which is vertical farming, to increase our volume efficiency. So for fuel production, we combine local carbon dioxide from the atmosphere that we brought from Earth, overheated catalysts. And then we essentially then split the water using electrolysis, I think.
The crew. The mission will not only need just the best equipment, but also the best crew to guarantee mission success. Everybody will undergo mandatory medical training to stabilize crewmates in critical moments. First, the commander, who is the pilot and will be landing the ship on Mars. He is also going to monitor the crew's mental health and drive the rover. Next is the chief mechanical engineer. He's going to monitor the habitats, give inspections, and set up the power grids. Next is another mechanical engineer to manage the heavy machinery, such as the 3D printing robot and the rover. You also do maintenance on the airlocks. Fourth, a geologist to explore the Tharsis region. He will deploy the rovers to explore the Tharsis region. Next, a geologist to enter the lava tubes to check stability and locate ice resources in future areas to build more habitats. And finally, a astrobiologist to evaluate samples of life signs and manage the greenhouse to produce the food.
Is that the end?
Yes.
Okay, thank you. Is the next team here? Eric, Isaac, and Calvin? I see.
Yes, we are here.
Okay, you are here. On my schedule, I put 3:55 Eastern, and it should have said 3:45 Eastern. Will you guys be ready in 8 minutes?
Yes, we will be ready in 8 minutes.
Okay, so we'll see you all in 8 minutes.
Hello and welcome to everyone joining us from around the world. We are the Dow High Mission to Mars group, and thank you for tuning in to listen. The primary purpose of this mission is to survive and explore Mars for 18 months while maintaining the health of astronauts within the environment of Mars, remaining free of severe negative health effects. The secondary mission is to explore Mars for geological, biological, and future in situ purposes. To achieve the Mars mission, the assumption of technological advancements will be possible within the next 5 years. All methods and materials will have scientific bases behind them to ensure the success in the Mars mission. The primary priority will always be focused on the safety of the astronauts over all other objectives in the Mars mission.
One of the most important parts of the whole mission is the crew. For the crew, we selected 3 astronauts with complementary expertise, and they would be aged 35 to 40 with excellent physical health, and would also be around the height of between 1.5 to 1.65 meters. So that way, they're not too tall and we are able to save resources. They would have strong teamwork, adaptability, and communication skills. That way they're able to work together rather than competing against each other. And they would be high in conscientiousness and low neuroticism. Conscientiousness high consciousness is being organized and responsible, and low neuroticism is being calm and emotionally stable. Now, they would also need to have diverse skills and coping mechanisms, and only one of them can be a leader. If all of them are leaders, they're going to compete with each other, and that's going to cause issues on the mission. For the mission roles, we will have one commander and medic. The medic will lead the crew, and he will oversee safety and provide medical care, as he's the one who most likely knows what's going on and cares most about the people. Then we will have an engineer that will focus on mechanical, electrical, and chemical engineering, and he will maintain the habitat, life support systems, power systems, and robotics. And finally, we will have a pilot in case we need someone to manage navigation systems, and an astrobiologist, which will operate the spacecraft and rovers, and they will also conduct geological and life detection research on Mars. For the mission training, they need to meet the NASA requirements, and the NASA requirements require them. First, they need to be a U.S. citizen or permanent resident. They need to be between 30 to 55. They need to have a master's degree in STEM field and 2 years in a STEM job, and pass the NASA long-duration flight astronaut physical. They need to have habitat operations and maintenance training, emergency response training, resource management training, simulated spacewalks training, and much more. Once they are able to meet that, they also need to become compatible with each other. They need to have diverse technical skill sets and strong communication and conflict resolution, and they need to trust each other, and they can't have any previous emotional connection, as previous emotional connections could cause issues on the mission. Right. Now, for the mental health, there are several challenges because there's isolation and homesickness from Earth, and there are 22-minute delayed communications with Earth, and there's limited living space and privacy, and due to the overview effect and the long mission duration, there's a high stress environment up in Mars. So for this, we plan out several solutions. There's daily exercise and structure routines. This exercise is proven to help with mental health. They're going to be able to communicate with family privately when possible, so there's nothing going on. And then we will do recreation and virtual reality and plans to improve the morale, so it feels more like Earth and not like a distant planet. And finally, we'll have conflict resolutions training, and we'll have regular crew check-ins, so we know all of the crew feels great. And for mission autonomy, given that we are on Mars and there's only 3 people on Mars, we will need AI assigned diagnostics and task planning, and we'll need to repair equipment using onboard tools and spare parts. We won't be able to receive help from Earth. And the commander needs to make immediate decisions when Earth cannot respond quickly, so if there's an emergency, and this is tasked to the medic. And finally, the crew will be trained to solve emergencies independently rather than relying on mission control on Earth. And for resource independence, we will extract water using the ISRU if necessary, but we'll recycle materials, as we will explain later. And we will also recycle waste for fertilizer, and we'll grow fresh crops there to maintain good health and to keep food. And we'll utilize kilopower reactors and solar panels for continuous power.
The selection of a landing site is a crucial part in the primary mission of ensuring the safety of all astronauts. Due to that, a criteria for the landing site has been established and includes selecting a landing site that maximizes astronaut safety, such as having a stable and known terrain, and offering protection from natural dangers. It should also provide accessible resources for long-term habitation, such as water, as well as offering scientific opportunities to investigate Mars water, geology, and potential for past or present life. And on the next slide, we have decided to use the S1094b crater, also known as the Christmas crater, at a diameter of 150 meters as our final base location. The crater has an advantage of being the closest surface ice to the equator, allowing for large amounts of water to be harvested. Located on the Amazonas Planitia, the crater is located 23 meters under the already low -3 to -4 kilometers datum. This allows for much less radiation to travel to the habitat location, while also reducing the effect of dust storms on the habitat as the crater is deeper in the ground. The crater also has secondary craters in a radius around it of 37 kilometers, which allows for development of future infrastructure. The ejection trajectory also shows that the ice is from Mars, giving an opportunity for future research and usage. The crater also allows for additional study as it is a crater created on December 24th, 2021, giving us access to a further deeper exploration of the geological process that forms when a crater is created, as well as the layers in the Martian ground, as it is a very young crater. The Amazonas Planitia, where it is located, also serves as a location of interest, as it is a potential area in where both floods and volcanic eruption and landslides could have changed the geography, as it is a very flat planitia. While the location theoretically provides less raw radiation protection, the lava tubes, the lack of understanding of lava tube compromises safety, which is our main priority. The walls of our habitat are also able to reduce the amount of radiation in a manageable amount, even in the relative open. Additional locations of nearby interest for study is the Medusa formations with potential to contain ice, the Tudun crater, which is extremely large and old, surrounding area of Christmas crater in order to locate more ice sheets, the Marta Valles, which connects the Inisum plain and was potentially where floods came from, and the Nucus Soki to studies on large landslides which came out of Olympus Mons. Furthermore, locations of metal-rich basalts, as well as locations for future exploration and colonization, will be located by astronauts. For the next slide, it explains our research goals. Our research goals is the secondary goal of exploring and researching. The first category is for biology and astrobiology. The second category is the geology, and the third category is the in situ research. For the first category of biology as well as in situ research, we need to investigate ice deposits in S194B crater, measure atmospheric water vapor, search for accessible groundwater, analyze regolith moisture content, study deep groundwater interactions with the surface, investigate ancient water sources for fossil evidence, search for past or present microbial lights. These investigations support whether Mars once supported life, as well as giving us knowledge of where resources are for future missions. Some tools that will be needed is Winky drills, ground penetrating radar, light microscopy modules, sample analysis at Mars, also known as SAMS, robotic rovers, kilopower reactors, solar panels, core sample collection system, stereo sample containers, communication system, onboard computing, and data storage. And then on the next slide, it'll explain more about the geology as well as more in situ resource development. So for this, we will need to identify resources for human settlements, such as characterizing the Martian geology and surface materials, evaluating resources for in situ resource utilization, reconstruct Mars geological and environmental history to determine where resources are. Geological investigation includes analyzing regolith compositions for ISRU, identify contaminants in Martian water and ice, locate volcanic basalt deposits containing useful metals, compare deep regolith with radiation-exposed surface soils, evaluate regolith most suitable for agriculture, and planetary history includes studying lava tube formation and comparing with Earth's or future missions. And on the next slide, it will be on the next slide. Will be where the scientific equipment is explained. The scientific equipment needed includes the basic lab equipment as well as things such as the Winky drills, ground penetrating radar, night microscopy modules, sample analysis at Mars, robotic rovers, kilopower reactors, solar panels, core sample collection systems, stereo sample containers, communication systems, onboard computing and data storage, and radiant georadars, X-rays, drones, microfluidic RNA and DNA samplinizers, Category 3 contaminant cabinets, laser-induced fluorescence spectrometers, and the more. Some of the most important of these are the Winky drills, which are essential for drilling and finding future resources. Night microscopy modules, which can see down to 2U of any material, allowing it to help in all three categories. Radiant georadar to look underground for possible liquid water and other formations, as well as the sample analysis to measure water content, detect gases and organic compounds, as well as analyze samples for potential biosignatures. To start our engineering section is the habitat and mission equipment slide. For this, the sample analysis at Mars will be built into the habitat, and the power system is able to produce excessive electricity to ensure our astronauts always have electricity and stay safe. The habitat is protected by 6 layers of materials and is 1.1812 meters thick. 1 meter of Martian regolith is able to help block radiation, while a layer of titanium under it is able to keep structural integrity. The third layer of lithium 6 brohide tin is effective radiation shield, while aerospace aluminum gives further integrity. Between that is also a silica aerogel to ensure insulation. The radiation amount over the whole span of the mission will go from 133.9 MSV to 49.6 MSV in 18 months, which is less than the amount experienced by ISS crew members, which allows our crew members to stay safe. For the next slide, the power generation will be explored deeper. It is an essential factor in survival, and our main power generators will be 3 separate kilo-power nuclear fission reactors with a total output of 30 kilowatts. Each reactor is located more than 1 kilometer away from the main habitat in separate secondary craters. This ensures astronauts will remain safe from any malfunctions that happens, as well as radiation outputs, while also ensuring no chain reactions will happen if one explodes. The priority of where this power goes is always to life support to ensure our astronauts will remain safe. Excess energy will go to charge the scientific equipment as well as power from the solar panel rays, which is 200 meters of flexible solar panels in order to fit on any terrain. And for the next slide.
As previously stated, the safety of our astronauts is of the highest priority to us. So we took a lot of care in arranging the life support systems. For oxygen generation and water recovery, we have we've put in a Sabatier reactor electrolysis loop, where, as explained in previous presentations, water, 2 electrodes are placed into water, a current run between them, splitting the water into the base components of oxygen and hydrogen. In previous models, such as the oxygen generation assembly on the ISS, these bubbles were pumped out using heavy pumps and centrifuges, but we used an experimental unit designed by Georgia Tech called the Magnetohydrodynamic Oxygen Generation Assembly, where the bubbles, where a ring of magnets is placed around the water tank, and the bubbles are essentially centrifuged out. Then the excess hydrogen is fed into a Sabatier reactor and mixed with carbon dioxide taken from the carbon dioxide removal assembly, which scrubs the carbon dioxide from the air and places it into the Sabatier reactor to create water and methane, which can be used for additional fuel. And then for waste management, there's a lavatory which automatically seals away and sterilizes feces, and then filters the wastewater to be further used by the astronauts.
Right. So we will either We will extract water from Martian ice using ISRU if necessary, as stated, but we will mostly recycle wastewater with a 98% recovery expected, according to ISS statistics. And since approximately 6 liters of water are used per astronaut per day for drinking, hygiene, food preparation, experiments, and more, that means we don't need to bring that much water. And so we predicted it to be 1 metric ton of water just in case, as we can also produce water there. And for now, our primary diet will consist of freeze-dried food, dehydrated, thermostabilized, and vacuum-sealed foods. And it is designed to remain safe for the 1.5-year mission. And we also grow fresh crops, including lettuce, spinach, radishes, basil, and green onions, as those have proven to be some of the most resource-efficient plants to grow, as they don't take up that much space and that many nutrients. And they will also provide vitamins, dietary variety, and they will help improve crew morale. And we will feed a lot of food, such as bread, meats, and all of that, and use those processes to make sure that the astronauts can eat them and they can last for 1.5 years. And for waste management, we will recycle wastewater into drinking water using processes that my partner has listed. And we also process organic waste into fertilizer, and that can be used on plants. And we will compact and store non-recyclable waste to store it as a lost state that we cannot just dump the trash on Mars. And finally, we will seal medical waste to prevent contamination. And for crew health, the crew is expected to do 2.5 hours of daily exercise, such as resistance and cardiovascular training, as NASA states for their ISS rules. That way, they not only stay with good mental health, but they stay fit, as the gravity is weaker, so that they will grow weaker if they don't do exercise. We'll also continuously monitor their health and do medical evaluations. The medic will obviously do this. And finally, we'll maintain physical and mental well-being throughout the whole mission by making sure they can train and they have time to relax, and so that they're not as stressed out, because we want to ensure that our crew is happy throughout the whole mission. As the happier they are, the more efficient they are. Right.
As for our habitat will be delivered off of these spaceships in roughly 2 by 2 by 2 meter modules, as shown in this this diagram. The first one will be suit storage, as well as holding all of the life support systems that I mentioned earlier. In the second one will be food storage and water storage. Though both of those will be stacked on either side, and the space in between, because of the amount of material, can be used as it will double as an emergency radiation shelter. In the third module, there will be the greenhouse, as well as the lab station for running all of the experiments. In the fourth one is the residential module, where there will be 3 beds, 2 to one side, 1 to the other. Under the one on the other side, we will store the mini treadmill, as well as the resistance training equipment. And this slide also goes further in depth into those modules. And then as for the bots that we will be taking up, one of them will be a Regolith 3D printer, similar to this diagram here, except mobile and with an intake, so it can take in the Regolith from the Martian surface and then pack in roughly 10-meter layer lines, similar to a 3D printer, around our habitat to protect from more radiation. On top of that, there will also be a construction bot, which has tow cable capabilities, as well as push pads. So these will be able to push those modules together and then weld each module shut, and then go into the module and caulk it shut with a special airtight caulk. Finally, we have the surface exploration vehicles, where we will have one pressurized vehicle right here, designed by NASA for specifically for this purpose. We also have multiple unmanned rovers going out, retrieving samples, as well as drilling into the ice for purification and use by the astronauts. And finally, we have our mass budgeting. As you can see from this table, our final weight came down to 29,666.81 kilograms, giving us a margin of roughly 340 kilograms. Thank you all for listening. Thank you.
Thank you very much. Great presentation. And I just want to say to Amethyst and your team, I know you lost electricity, if you want to record your presentation and email it to me, I will post it with the others. It's not your fault the electricity went out, so please have that to me by tonight if you possibly can. Thank you very much. Okay, next team, final team, if you are here.
Yes, we're here.
Okay. Calvin or whoever. Okay, there you go. Thank you. All right, next team, you may share your screen and we can get started.
Okay. Can you see my screen?
Yes.
Okay. Hi, my name is Miriam, and my teammates and I, Asa, Pari, and Jayan, came up with a manned Mars mission design concept built around sustainability, expandability, and scientific exploration, and we named it RED Initiative. I think our team actually met each other for the first time on the first day of the competition. And so I guess connecting with people from the other side of the world over a shared passion has been very exciting when writing the report together. So right now we're going to go through a very brief presentation overview. So we're going to start off with mission characteristics, followed by the three major parts: engineering, human factors, and science. So first off, we have our mission objectives. Obviously, our primary objective is to set up an initial habitable and expandable base on Mars, followed by a crew to conduct scientific research on the planet. And our secondary objectives would be that following the success of this mission, we would hopefully increase funding and public interest towards a long-term human presence on Mars and just increase our understanding as a human species to our place in the universe.
A wonderful introduction. So now we're going to move on to the areas of expertise among the crew members. So first we have our leader, who's also going to have a specialty in nuclear engineering. Basically, obviously, as a leader, they're going to take control of like decision making, making sure schedules get followed, all that stuff. And of course, they're going to be in charge of the power source, maintaining that, along as in situ realization of fuel and oxygen. Mostly, they're going to focus on cooperation, resolving difficulties, things like that. Followed by the aerospace engineering specialist, who also has a specialty in software integration. Basically, their job is to maintain like critical decisions, stuff like that, make sure cargo is utilized properly, and make sure their problem solving skills can be used to the best of our mission. Next up, we have a nutritional psychologist who I don't know why it's not included on the presentation, but I believe this person also is a trauma surgeon. Correct me if I'm wrong. But their scientific purpose is they're going to be studying human behavior, mental health, and making sure we keep in contact with Earth about astronauts' health. And as a trauma surgeon, they're going to be handling like gruesome injuries, but all members of the crew are trained in field medic actions. And the next specialist we're going to have is geology with a focus on paleontology. Obviously, we want to study the way Mars was in the past, is now, things like the way the weather affects it, what sites are going to be best for future settling, and identifying potential life in the past. That's where the paleontology part comes in. Followed by our final specialist, which is molecular biology and botany, specifically like astrobiology. And their main work is going to be in the greenhouse. They also have an experiment they're going to be maintaining throughout the mission that we're going to get into later. But their job is to handle, actually living things as the paleontologist handles things that were once living. And our final crew member is not a human at all, but a humanoid robot that has been pre-trained on simulations of what it might seek to expect on a mission like this. Obviously, it needs to know food, water, therapy, anything like that. It just needs a power supply and will mostly be relegated to moving things around, small tasks like that. Obviously, it can get in there like the airlocks much quicker than a human can and can do minor tasks in and around the habitat. And that concludes our crew section. So we're just going to move on to the mission overview here. So we divided it into 3 phases, where phase 1 launches in September 2035 and phase 2 follows shortly after in October 2035. We chose this because there wouldn't really be a better date, considering this mission can only be 1.5 years long. So there's only going to be about 2 to 3 weeks for phase 1, which is fully autonomous to establish habitat, power, and communications on the Martian surface, before phase 2, humans land and begin scientific exploration, maintenance, and only things humans are more specialized at, like scouting out potential locations for the future. And phase 3 is that future, where we're going to be looking at future locations to settle, how these experiments have impacted our understanding of the planet, and how we can develop stronger infrastructure to get a sustained human presence on Mars. And finally, we have our landing site as the last part of the introduction. Right here at 18.27 north, 77.24 east. Doesn't have a special name. We just chose it because it is reliably flat. It has a high proximity to Jezero crater, which is going to come into play in the science section of this presentation. And also, according to swim data, it has a high consistency with subsurface. So astronauts will be able to get liquid water. And you can see it right there, along with the swim data. Our habitat is that little green circle. And if you can see that white triangle on the right, that's the Perseverance rover that's going to come into play later. We can go on.
And now we're going to start with the engineering section. So this is what Mia and Jayan actually worked on, but unfortunately, Jayan couldn't join us. So I'm sorry if some of her parts I'm not able to explain in as much detail as she would. So first off, we have the power. Of course, any Mars mission needs power supply, and for that, we chose nuclear fission. Why? Because it is arguably the most efficient choice from the standard engineering perspective, as it has far less limitations than traditional renewable energy sources. So we're actually going to use nuclear fission in 2 different ways. So first of all, we're going to have 4 10 kilowatt kilopower nuclear generators, which essentially work by converting heat from the solid uranium-235 reactor. And we're also going to be using Stirling generators. Now, Perseverance and many other spacecraft actually use multi-mission thermoelectric radioisotope generators. But actually, research has shown that Stirling generators are so much more efficient. And there's a lot of research going on right now about how they can be used for spacecraft. So from now until 2035, we expect a lot of tests to prove that we could replace these generators with the Stirling radioisotope ones, because they are significantly more efficient. And of course, we need to communicate with Earth. Now, we do have the Mars Relay Orbiter, which is a set of 4 satellites orbiting Mars, but they're not enough to really establish a stable connection, which is why, assuming it is operational within expected time frame, our mission will rely on the Mars Telecommunications Network, and preferably on the Mars Planetary Network. Now, the Mars Planetary Network does include the Mars Relay Network, or at least 1 relay orbiter connected, and the Mars Surface Network, which in other terms is the habitat, which we will get to later, and finally the Earth Network, which includes the Deep Space Network. So this diagram shows 1, 2, 3, and 4, the 4 relay orbiters, and a hypothetical habitat along with the Earth Space Network. So this is what we're hoping to establish for our communications. Now, another very important aspect is the way we're monitoring weather in our mission, because we know that the location we pick does have dust storms, and they can get regionally big. And even if they didn't, we still think that forecasting weather is very important in any Mars manned mission. And this is why we're thinking of doing it with CubeSats, and specifically a constellation of 10 3-unit CubeSats. Why? Because this specific technology is actually being tested on Earth, where NASA is researching how 3-unit CubeSats can be used for reliable weather data on Earth. So we assume that we can also use this on Mars. And actually, CubeSats have already been sent to Mars, so we know that this technology works through NASA's Marco A and Marco B CubeSats that have been sent. So we want to establish this constellation, which in total would only weigh 60 kilograms. And we find it super important because even though we have satellites that give us weather data about Mars, it's not continuous like we want it to. So we need to know in real time what could happen to ensure crew safety and also to plan out short-term and long-term expeditions. Now we have the main habitat breakdown, which should be stable on the ground and integrated with the Martian landscape to utilize regolith for radiation shielding. So you can see this module view that we made where we picked the hexagonal shape for the habitat with 7 modules. So you have the main control module with other modules that are essential for humans, like the gym and mental reset, the cabin, the science lab for the science section, and obviously the greenhouse and food storage. Because we wanted this habitat to be expandable, so even after the mission ends, we want this habitat to actually help future missions and not just stay there and just get dust on it. So we would need to automate remotely operated robots to perform the initial setup, and they would have to be multifunctional functional robots. And we would also we needed to be structurally protected for future expansion by incorporating TransHap-inspired layering to defend against micrometeoroids, for example, and making it scalable through inflatable modules, etc. And we also need the airlock and suit ports. I didn't really work on this part, so that's why I might not explain it very well. But essentially, this is how astronauts go in and out of the habitat. So you would have a full-on operational sequence with docking and sealing, followed by hatch alignment, pressure regulation, and either astronaut ingress or astronaut egress. So you can so these bullet points, they kind of explain what's going on in the suit port 3D rendering. And that's essentially it. And because we have a habitat that's integrated with the Martian landscape, we also need to talk about regolith mitigation and the challenges that we have with current internal air filtration challenges, which rely on continuous air cycling, leading to prolonged clearance times. So we are thinking about using electrodynamic dust shield, which you can tell here that after activation, they actually make the regolith go away. And now we're going to talk about the realization of essentials. And so we're going to start off with the oxygen production. So we're relying on the MOXIE experiment on NASA's Perseverance rover, which has successfully produced oxygen from Mars's atmosphere. And it was able to produce 12 grams of oxygen an hour, but we obviously need more than that. We need between 0.8 and 0.9 kilograms of oxygen per day. So it would have to be a lot bigger. And actually, this type of large-scale MOXIE system would need its own kilopower nuclear reactor to work. And here you can kind of see how it works. And of course, we would also need a water recovery system. So we decided to be inspired by the one used on the ISS. So you got the urine processor assembly. So astronaut urine would be used would be recycled for drinkable water. And you would also have the water processor assembly for that as well, so that we don't have to take a lot of water from Earth, and then it would make the mission impossible. And of course, we also need to make propellant. So for that, we know that the reverse water gas shift and the Sabatier reaction combined with water electrolysis are the most effective. And the Sabatier has over 99% CO2 conversion. So this is why we chose it. So that because if we didn't have it, then we would need to bring more than 33 tons of propellant with us, which would not work for the mission, considering constraints. And now we're going to get into the vehicles that we have. So we have 2 main vehicles. We have the unpressurized Martian vehicle for exploration, and we have the pressurized one. This one is inspired by the one used on the Apollo program, the lunar rover vehicle. And essentially, this rover would be used for short expeditions, and it would include optical and thermal cameras for high-resolution imaging of the planet and the night sky, ground-penetrating radar for subsurface ice imaging, and a robotic arm for sample grasping. And in addition to these science instruments, we also want to include the autonomous navigation technology used on Perseverance to map its own route, so it would help astronauts safely explore other regions. Same thing for the pressurized rover, similar technologies. This one is for long-term expeditions that would be precisely mapped out. And also, in case of emergency, it would act as a secondary mobile habitat for 2 people. And it would also utilize its own modular nuclear Stirling generators as the primary power supply, like the one used on the unpressurized rover. And here we're just explaining the new technology being tested by NASA, which are the mesh wheels. So we would like to integrate that on the pressurized rover and the unpressurized rover. And last but not least, for the engineering section, we've got the Rocky assembly and exploration robots. So these are essentially hexapods, and we want to bring 10 of these on the surface of the planet. And the thing is, these are so much more efficient for searching life than rovers because they can crawl and fit into tiny spaces. So we want to get 10 of these, and obviously it has to be compact and lightweight and have flexible legs.
Okay, now for human operations, the systems and strategies that support the crew on Mars, including astronaut suit designs, physiological health, psychological health, nutritional plans, hydroponic system, medicine and emergency plans, and the greenhouse design. The Martian Extravehicular Exploratory Unit, or MEU, is based off of the Axiom Extravehicular Mobility Unit made by Axiom Space. It has 3 layers, the outer layer, insulation layer, and the LCVG, hard components including the helmet and visor, gloves and boots, and the PLSS, and the structure is the PLSS backpack made of lightweight aluminum, which is attached to the suit with hinges to allow for rear entry design. This design was specifically chosen to prevent tears and abrasions, maintain pressure and temperature, filter toxins, and protect the astronaut. Each Martian astronaut will have their primary suit, so 5 suits, and 3 extra MEU suits will be taken in case of emergencies. For physiological health, to combat the effects of microgravity, the daily MarsFit regimen ensures crew health. Each week, it targets cardiovascular endurance, flexibility, and mobility, while directly counteracting bone and muscle loss to keep astronauts fit for surface operations. Here's a 1-week example of the MarsFit regimen. Each day includes a regimen ranging from 60 to 90 minutes, including a 20-minute recovery and reset day on Sunday. The MarsFit schedule includes some exercise machinery that have been used on the ISS. This includes the Arid, the Colbert, and the Ceres. For psychological health, to solve and prevent psychological effects of isolation, such as the Earth out of view effect, depression, and the us versus them ideology, we use many resources already in the habitat to make the astronauts feel as comfortable as possible. Some solutions to mitigate homesickness includes VR goggles to view Earth destinations, plants and flowers around the habitat, decorate the habitat during holidays, communication with friends and family, and bringing their favorite hobbies. To counteract depression, having Martian astronauts spend time together prior to the mission on Mars, they can get used to experiencing any altercations between themselves and solve them before having the mission on Mars. The MarsFit schedule also includes yoga and meditation that mentally relax the astronauts. The stress reduction theory and the attention restoration theory say that watching plants grow also relaxes the mind and regulates emotions. To counteract the us versus them ideology, the phenomenon usually causes many altercations between mission control and astronauts. To avoid that, astronauts can be given more freedom when deciding their daily schedules, being given a to-do list for every day instead of time-specific schedules. They also get freedom to pick their food and vegetables during meals and have a little bit of freedom in their exercise schedules. For nutrition plans, an astronaut on Mars needs to consume an average of 2,800 to 3,200 kilocalories per day to maintain body mass. This sample one-day menu combines packaged rations with fresh greenhouse fruits and vegetables. It delivers 3,048 kilocalories, providing the high energy required for heavy physical activity and demanding EVA missions. To prevent meal fatigue, gourmet and comfort food options chosen by the astronauts help mitigate feelings of isolation. Here is a nutrient requirement breakdown given by NASA that we based our meal plan off of. This is the hydroponic system we designed called the Mars Sustainable Hydroponics Open Air System. It is a shelf system, and there will be 4 MSHA shelves, each with different groups of crops based on the pH levels the plants need to grow most effectively. For example, lettuce, jalapenos, and cherry tomatoes will all be on one shelf due to them all needing a pH of 6 to 7. Other experimentation will be done with the treated regolith for soil that will be explained later. For surface safety, our emergency protocols are a large supply of medicine is necessary to manage emergency injuries, environmental stressors, and physical problems to ensure crew safety during Martian operations. This includes antiseptics and antibiotics, disinfectants, dental, anesthetics, anti-allergens, and supplements taken by the astronauts to ensure health. For surface safety, our emergency protocols rely on a mandatory buddy system for all EVAs and the designated emergency lockdown shelter. Medical emergencies are managed by the trauma surgeon with help from the humanoid robot, and isolation quarantines protect the habitat from external contamination. To prevent using an excessive amount of electricity to power heavy-duty LED lights, a transparent inflatable greenhouse design allows the astronauts to preserve energy and also test crop growing in natural Martian environments for future settlement research. The design uses Teflon FEP as that takes most of the environmental stress, colorless polyamide layers for structural strength, Kapton E for structure and heat resistance, and Torlum as a UV filter to block harmful radiation. A multi-layer insulation MLI blanket will be used to reflect the thermal energy from the greenhouse system back into itself during the cold Martian nights. During the day, it will be folded and rolled tightly around the base of the dome. When heat sensors detect temperatures below the comfort zone, mechanical rollers will follow the tracks around the dome and cover the clear structure in the insulation.
Wonderful. We're going to move on right here to our last section, which is science. As you can see here, we have 8 broad topics, which I'm not going to read to you now because we're going to go over them.
Just to be fair, excuse me one moment. You have to wrap up in the next 2 minutes.
Thank you. So first, we're going to have Perseverance sample retrieval and study. There are 21 samples currently on board the rover. It can reach the habitat in about 38 days. Step 1, analyze the witness tubes to mark contaminants. We're going to use a glove box that mimics the Martian environment to analyze the samples to preserve them, and we may return them to Earth. The astrobiologist will be notified if the geologist detects any signs of life, physical or chemical. Next slide. The next thing is going to be for the integrity of future Martian missions, which is confirming the SWIM data, or the Subsurface Water Ice Mapping Initiative. So basically, we're going to go collect 5 samples from a distinct site spaced 5 meters apart. If they all have ice, we confirm the site, we move on to the next one. Makes it where in the future we don't have to do this again, and we can just rely on SWIM data, or we can fix the methods by which we gather it. Next. Geologic studies. This is basically just analyzing the ways Mars was in the past and locating potential resources that are going to be very helpful for future settlements. So as you can see in these pictures, this is a ground penetrating radar. And on the bottom right, that's our specific location, the northwest region of Jezero Crater, which has a large concentration of carbonates and iron in a hydrated form. Next is attempting to mutate methanotrophic microbes to produce methane on the surface. So basically, a lot of methane producing methods have a lack of scalability. This method has been shown to be scalable in a Penn State study. But basically, our secondary goal is to mutate these bacteria to handle Martian surface conditions so we can install the cells on the surface. This is definitely our most theoretical of the experiments, but it would be very important if it's successful. Next right here, laser-centered concrete. The pictures right here on the left are from lunar tests, but we believe this can be extrapolated over to Mars. We're going to use a CO2 laser apparatus to fuse the soil, create a 1 by 1 meter platform using a rover. The rover is going to take pictures, small and large, and then drive over the patch repeatedly and document any damage that it incurs.
Okay, you got about 10 seconds. Wrap it up, please.
This is a step-by-step plan on how to make Martian regoliths safe to grow plants. Next. Here's how to do maintenance.
And finally, we've got the mass breakdown of everything, which comes to a total of almost 26 tons. Thank you so much for listening, and we hope you enjoyed.
Thank you so much. And just to let you know, your slides will be uploaded to YouTube, all these presentations. It's going to take a while for it to process and get uploaded. So I will be sending out an email. We are starting our critiques a few hours later than our presentations, and the schedule will be much tighter. So make sure that you are ready with your critiques and they are outlined very clearly. If your team is not participating in critiques, please let me know and I will remove you from the schedule. I hope to see you all Wednesday. Great job, everybody. We will start at 1:30 p.m. Eastern Time, which is 5:30 p.m. UTC. So I will see you all Wednesday and I will be emailing you later today.